Good evening, all of you. Bhaskar, why all phase voltages are same? Because all having same turns, no? Same turn, same flux, so same phase voltage. Okay. In the last class, we have seen lastly about EMF equation of three-phase transformer. So while calculating K particularly, you should use while calculating K transformation ratio, you should use the phase voltages or phase turns or phase currents only. Okay, but only in three phase we have that phase and line concepts, but single phase you don't get all this. Take care while doing three phase calculations. Line voltage depends on, Bhaskar, are you aware of first network theory clearly? See, each and everything we cannot give here because network theory will give the basics of delta and star connection. So again we don't, I cannot give here because it will take so much time now. Again already it is itself so much time. So it cannot give all that relations in star and delta. You should know the phase and line voltage relation for delta and star and currents. Okay. Phase voltages depends on what? Phase voltage in three phase transformer depends on number of turns in each phase and flux in the core. What is the turns in each phase? If you design a three phase transformer, the three phases we will design with same number of turns. And flux will be same for anyhow because same magnetic material, same flux will flow. So EMF per phase is same for every phase in three phase transformer, but line voltages will change. That depends on connection, whether it is star connected or delta connected. If it is delta, line voltage is same there. Line voltage is equal to phase voltage only. But if it is a star connection, line voltage magnitude is root 3 times of phase voltage. Okay, for star it is like that. Line voltages changes. No need to start network theory here. Already in your engineering, at least it may complete now about delta star connections. In the first year itself, mostly network theory will come. Interest current all you will get in switching transients. Wait up to that. See, actually here you don't get like sequence first. First we need to teach only mathematics like that. So that depends on batches, whatever. So I'm not talking about here. You should complete already completed for each and every student in engineering. No, that is in the first or second year itself. Mostly network theory will be completed. See the question first. If the primary line voltage rating is 3.3 kV star, see this is a three-phase transformer, primary star connected, secondary delta connected. Okay, primary star, secondary delta. Now primary line voltage given. Primary line voltage, what is that? V1L. Primary line voltage V1L equal to 3.3 kilovolts. Start side, that is. And kVA rating of this transformer is 25 kVA. Okay. Per phase turns ratio. Per phase turns ratio means N1 by N2 per phase. Turns ratio means N1 by N2. So directly they mention per phase it is. That value is 5:1 or 5:1. Then line current rating of the secondary side. We need to find line current rating of secondary side. Okay. We need to find secondary line current. Okay. So those who are not aware of the star delta, you just take these relations. In delta connection, what is the line voltages and currents relation? In delta, line voltage, phase voltage, both are same. Okay. Line voltage both are, phase voltage both are same. And line current in delta is what? Line current, √3 times of phase current. Line current is √3 times of phase current. Similarly, in star connection, what is the line voltage? Line voltage here, opposite to previous, line voltage is √3 times of phase voltage. Line voltage in star connection √3 times of phase voltage, and line current in star connection equal to phase current. In star, phase current, line current both are same. In delta, phase voltage, line voltage both are same magnitudes. Okay, remember this. Now we need to find secondary line current. How to find secondary line current? Just now I said previously in the transformation ratio. While using transformation ratio, what is the relation you have to use? Either anything, voltage, turns, currents, anything you can use, but phase only. If we use turns ratio, what should be? N2 phase by N1 phase. And here E2 phase by E1 phase. Secondary voltage by primary voltage. E2 phase by E1 phase. Or this is equal to I1 phase by I2 phase. Just like single phase transformer only, there we write directly N2 by N1 equal to E2 by E1 equal to I1 by I2. But here while writing we should mention phase, because every time we should substitute phase only. This is phase transformation ratio, not line transformation directly. So use this equation relation. We have N1 by N2 relation and we need to find current relation. So you have to use N2 by N1 equal to I1 by I2 relation. N2 by N1 is there. If you find I1, or if you know I1, I2 you will get. So from this, I1 phase by I2 phase is equal to N2 phase by N1 phase. These two I am equating. Any two you can equate, because we know these number of turns and these currents. That's why I am using this. If you know I1, I2 you can find. N2 by N1 is there already. What is N2 by N1? N1 by N2 is 5 by 1. Then N2 by N1 is 1 by 5. Now I1, if you calculate E2, you can, I2 you can find. How to find I1? So we have the primary line voltage and kVA rating. kVA rating is same on both the sides. That may be single phase transformer or three phase transformer, anything, kVA rating remains same. So use this kVA rating, 25 kVA, 25 into 10 cube. What is the kVA rating formula first? Write it once. kVA rating in three phase. How to write it is? Volt ampere means voltage current. For single phase, voltage current directly we take. But while writing three phase, what is the kVA rating? √3 VL IL. Line voltage, line current. Or one more formula. In terms of phase, if you want to substitute 3V phase, I phase. Anything you can use. In three phase, take care the calculations in three phase only, because mostly we do mistakes in three phase calculation but not single phase. While writing three phase, KVA rating is this one, 3 V phase I phase. So that 3 V phase I phase you can also write as in line root 3 VL IR. Both values are same. Anything you can use. But mostly we will utilize this one because in every problems the data given is line voltages, line currents. Directly we utilize this one. So easy calculation. You can use this is also if they given phase voltage, phase currents. But mostly we use this. Now using this relation, what is the KVA rating given? 25 into 10 cube equal to root 3 primary line voltage is there. How much? 3.3 K. And we need to find primary line current first. I1 L. Now calculate what is I1 L. How much? I1 L how much? Primary line current how much? 4.37 amperes. This is primary line current. Now check one time. Primary connection is what here? Star. Secondary connection is delta. So primary star means what is the primary phase current now? Primary phase current, line current, both are same. Means star connection phase means phase current, line current, both are same. So therefore, I1 phase equal to line current itself. What is the line current we got? 4.37. So phase current also same, 4.37 amperes. Okay, 4.37. Now substitute here. We need I2. Now I1 we have this N2 by N1 also we have. I1 is 4.37 divided by I2 phase. This is equal to 1 by 5. Calculate the secondary phase current. First you will get phase current. What is that? How much? Secondary phase current. How much it is? Phase current 21.87. Okay. So this secondary phase current 21.87 or 85. Somebody is getting 85 like this. So 21.87 amperes. Okay, secondary phase current. But what is the question they are asking? The line current rating of the secondary side. Secondary is what here? Delta. So in delta, what is the line current? Root 3 times of phase current. Therefore, the secondary line current is root 3 times of phase current, 21.87. Now, what is the final answer? Line current 37.87, right? 37.87 amperes. So this is the secondary line current. See, question is easy question only, but why they given it is for 2 marks again? There is more chances to do small mistakes in the calculation. And most of the people in this year, so they said they given the answer directly 21.87 by mistake, or that is in the hurry situations, people will forget what they need to give the answer, because if options are there, they may check. But in this type of question, so here we need to write numerical answer type question. No, so there some people written 21.87. They know because they did not reading the question properly. They know line current initially, but whenever they find this value, they will write 21.87 directly here. That is wrong. You should write 37.87. Line current is this. Okay, take care of these calculations. See, first in the question, primary line voltage given 3.3 kV and KVA rating of the transformer given, and turns ratio also given 5:1. We need to calculate a line current rating of secondary side. For that, we are using this formula, this relation. N2 phase by N1 phase equal to I1 phase by I2 phase. Why we are using this? Because N2 by N1 they given. That's why we are using this directly. Then if you know I1, I2 you can find. How to find that I1? Using KVA relation. KVA is what? Root 3 VL IL. And some of you may be asking it is how it is root 3 VL IL. See, single phase transformer. What is the volt ampere rating means? Voltage rating, current rating, V1, I1, that voltage current product. In three phases. So what is the volt ampere rating? 3 times of V1, I1. Because all voltages are same. That's why directly 3 times of V1, I1 we take. Now, this is what 3 V phase, I phase. Phase voltage, phase currents, 3 V phase, I phase. Now, how we are writing it is in root 3 VL IL. 3 into, for example, I'm considering delta. For any connection, same formula. For example, delta. What is the phase voltage, line voltage in delta? Same. So line voltage equal to phase voltage into what is the phase current in delta? Phase current. Line current is root 3 times phase current. Or what is the phase current? IL by root 3. Phase current is IL by root 3. Now root 3 gets cancelled, and one more root 3 will be available here because this is 3 now. Then root 3 VL IL. Or if you take star also from here, if you take star also, what is the volt ampere rating? 3 into what is in star connection? What is the phase voltage? Line voltage by root 3 into in star. What is the phase current? Phase current equal to line current. Both are same. Now again root 3 cancel. You will get root 3 VL IL. So that may be delta or that may be star. Anything, use this root 3 VL IL. Or 3 V phase I phase, that is also you can use volt ampere rating. Now clear? Next question. See this question. A three phase, important efficiency related it is. A three phase 900 kVA, 3 kV by root 3 kV voltage rating. 3 kV means primary line voltage, root 3 kV means secondary line voltage, and the transformer connection is what? Delta star. Primary delta, secondary star. If TS transformer has primary resistance per phase 0.3 ohm and secondary resistance per phase 0.02. So first the rating given is 900 kVA volt ampere rating, and the voltage rating is 3 kV by root 3 kilovolts, and the type of connection is a delta star, primary delta, secondary star. Primary resistance R1 0.3 ohm per phase it is. Okay. Secondary resistance R2 equal to 0.02 ohm per phase. Iron loss of transformer given 10 kilowatt. Okay. Now the full load efficiency of the transformer operated at UPF. So simply the efficiency at full load unity power factor is dash. This is the question. So already we are aware of finding efficiency for single phase transformer very well. Same as it is, we need to find. But little care required while doing three phase calculation. What is the formula? If you remember, tell me once. Efficiency at any fraction x full load. What is the formula? X into volt ampere rating cos phi divided by x volt ampere cos phi plus iron loss plus copper loss. X square copper loss. This is the formula. Same formula for three phase also same, but substitution, while substituting the values you need to take care, because what is the power output here? Three phase power, not only single phase power. Three phase. Now volt ampere means 900 kVA. 900 kVA for 3 phases it is. Okay. Now there is volt ampere. Full load means X is 1. UPF also given, cos phi equal to 1. Volt ampere rating also there, 900. So everything available. The only unavailable thing here in this question is this copper loss. That's it. X is 1. X square means 1 square, 1 only. Only full load copper loss you need to calculate. That's it. Only copper loss. That is only the important here. Remaining all directly there. Iron loss also given, 10 kilowatt directly. Only copper loss you need to calculate. How to find copper loss? Resistance values when you know, calculate the copper loss using this equation. Either I1 square R01 you can use, or I2 square R02. You can use any relation. Same answers you will get. Anything you can choose. I1 square R01 or I2 square R02. So let us choose I2 square R02. Okay. What is the current here? Rated current. R02 means what? Calculate R02 first. Calculate R02 first. What is R02? R2 plus R1 dash. R2 plus R1 dash means K square R1. Okay. R2 is there, R1 is there. What is the K first? K. How to find K? From the voltage rating, you can find K of the transformer. Transformation ratio. What is the K? Tell me. K equal to, how to write K always? Secondary phase voltage by primary phase voltage. That's it. Now, what is the secondary phase voltage? For that, you need to check secondary is what connection here. What is the secondary connection? Star. Secondary star connected. And given voltages always line voltages. Okay. Now, secondary phase voltage required. In star connection, secondary or phase voltage is what? Line voltage by root 3. So line voltage is root 3 kV. So root 3 kV divided by root 3. Don't confuse. Just I taken phase voltage. Line voltage by root 3. Now primary phase voltage. Primary connection is what first? Delta. So in delta, phase voltage equal to line voltage. So directly 3 kV. Now kk anyhow cancel. Now root 3 by root 3 is what? 1. Kk cancel, root 3 by root 3, 1. 1 by 3. This is the value of k. K is this 1 by 3. Now R2 is there, R1 is there. Calculate R02. R2. What is R2 value? 0.02 plus k square means 1 by 3 whole square into R1. What is R1? 0.3. 0.3. Now calculate this total. How much? R02. Rekha, we can use iron loss equal to copper loss at UPF. No. Because that is at maximum efficiency, iron copper loss equal to iron loss, but they are not asking about maximum efficiency. We need to find efficiency at full load UPF, but it is not maximum because they did not mention is it maximum or not. Okay, that's why follow as it is. Okay, right. 0.0533 ohms. 0.0533. Check all of you this. R02. R02 it is. Next, I2 we need I2 full load current because we need to find efficiency at full load. So calculate full load current I2. How to find I2? Same whatever we use single phase volt ampere rating by voltage. But to find I2, what is the formula? S by root 3 VF. This is a current line current I2. Substitute here 900 K. divided by root 3 into what is the secondary line voltage? Root 3. Root 3 into 10 cube. Then how much it is? 900 by 3, 300 amperes. This is a secondary line current. But whatever this formula I2 square R02 is there, this is the phase current here. Phase resistance, phase current. So secondary side, which connection? Star. So as it is star, secondary phase current is equal to line current. Since star connected, both are same. Okay. Therefore, copper loss. What is the copper loss formula? I2 square R02. But if you find only this, if you substitute in the equation, you will get the wrong answer. The thing is, don't forget to multiply with 3, because I square R copper loss for one phase. Like the total 3 phases, no? That's why in 3 phase always 3 times you have to take. Loss means total loss in 3 phase transformer, total copper loss. So 3 into 300 square into 0.0533. Okay, how much it is? How much? Yes, yes, 14 point, yes, 14.39 kilowatts. Yes, 14.39 kilowatts. This is the total copper loss. Okay, but most of the people may do wrong here is they will find only I2 square R02. They don't consider 3 times. Okay, I2 square R02 is the copper loss for one phase. There are 3 phases. That's why you have to take total 3. Then you will get total copper loss. Now substitute this loss in the efficiency. Therefore, efficiency at full load, unity power factor, X is 1, 900 into 10 cube into 1 UPF divided by 900 into 10 cube, and iron loss is 10 kilowatts, 10 into 10 cube, and copper loss we got 14.39 into 10 cube. Okay, 14.39. Now calculate what is the efficiency. Efficiency how much? Yes, 97.36, right? 97.36%. So this is the efficiency of this question. But if you substitute only I2 square R02, you will get wrong. 97.36 is right. Clear? You can find I1 square R01 also, you can find. Try this. If you want try, you will get the same copper loss. Anything you can consider. I1 square R01 or I2 square R02. Anything. Or if you want to find individually also, you can find I1 total copper loss is what? I1 square R1 primary side, secondary side I2 square R2. Then add both and multiply with 3. Okay, you will get total copper loss. Anyhow you can do. Yes, with respect to primary also you get same answer. Core loss already they given that whatever loss is given, that is for 3 phase only. So again you no need to multiply further. Okay. This is not maximum efficiency. Who said maximum? This is not maximum efficiency. Why x equal to 1? That is given full load. So x equal to 1. Are you forgetting? Now it's up. This is the most important thing. Learning subject is not important. So having that subject for long time, that is important. Okay. Yes, copper loss calculation, phase current only always, because resistance given per phase. So you should take current also per phase. Generally phase calculations only we do in 3 phase also, but you should take finally 3 times of that because of 3 phase. Okay, next question. See this question. This is also given for 2 marks, but if you properly understand, just 10 seconds is the answer. Quickly answer. Jadhav, if one phase has full load, other has different loads. So this type of things they don't give. Whenever they say full load means we have to consider for all phases it is. Otherwise, if it is different, they should give that. This phase is having this much load like that. Then you can find individually for each phase copper loss. Okay. This is not 3 single phase transformer. Okay, directly 3 phase transformer total iron loss they given. If it is 3 single phase, if they mention each single phase is 10 kilowatt, then you take 3 times of that. Transformer bank, then you have to take 3 times. Yes, efficiency maximum at 83%. Okay, anyhow. What is the answer for this? Yes, Pratyush, right. Yes, good, Deepak. So very easy question, right, Aishwarya? Option A is correct. Option A is correct. Actually, question is very big. They given so much data in this, but you no need to use all the data. Question is what? 3 single phase transformers are connected to form a delta star 3 phase transformer of rating 110 kV by 11 kV. This is line voltages, primary line voltage, secondary line voltage. The transformer supplies at 11 kV a load of 8 megawatt at 0.8 lagging power factor to nearby plant. Neglect losses, the ratio of currents. What is the type of connection first? See, primary delta, secondary star, 3 phase transformer. And the voltage rating of this given 110 kV by 11 kV. Okay. This is what line voltages. Always the voltage is given line. What we need to find? The ratio of phase currents. The ratio of phase currents in delta side to star side. Ratio of phase currents in delta side is means ratio of phase current I1 phase divided by I2 phase. This is you need to calculate. What is I1 by I2 in terms of voltage directly? E2 phase by E1 phase. That's it. E2 phase by E1 phase. Then I1 by I2 equal to E2 by E1. What this line, whatever voltage rating given, always E1 by E2 line. So what is E2 phase now? E2 phase secondary star. Secondary star line voltage 11 kV. So phase voltage is 11 k by root 3 divided by primary phase voltage. Primary side we have delta. What is the primary phase voltage? Equal to line voltage. Both are same. That is 110 kilovolts. Now kk cancel and this is 1 by 10. So totally 1 by 10 root 3 you will get. So what is the answer? 1 by 10 root 3 or 1 is to 10 root 3. So directly you will get. No need to solve more than this. The given load, according to that also you can solve, but it will be so much lengthy again. Based on the load given, you find secondary current first. Then if you know secondary current, you can find primary current. Then you have to take I1 by I2. So these are all lengthy process, not at all required. Simple question. Okay, clear all of it is. Oh, Jayant, we should express line voltage. No, K, that is we are equating transformation ratio na here. Transformation ratio always phase only. and they are asking phase current, primary phase current by secondary phase current. So as it is, whatever the answer you got, keep it is. That is itself the answer. Okay, right, no problem. But take care in actual examination. That's why here you should practice. Practice here, definitely you will get some mistakes here itself, but that mistakes you should overcome before examination. In the examination, you should not do for the well-known questions the mistakes, but 50% above students will do mistakes in the well-known questions only. Based on the load, see load given 8 megawatts. This is active power, megawatts, VI cos phi it is. So this is, what is the formula? Root 3 secondary side line voltage VL IL cos phi. Secondary side it is, because load is on secondary side. Now use this equation. Secondary line voltage is there 11 kV, power factor also they given, and from this you will get IL, secondary line current you will get. Then secondary phase current you can find based on the connection, phase or star or delta, that is. Once you know this, you can find primary phase current by using again same relation. Then I1 by I2 you need to tell. But anyhow, easily we are getting, then why should we go like that? Okay. Okay. Now we start three-phase transformers. Observe. Three-phase transformers. Three-phase transformers we started. Don't say that we already started. Yes, we started. Now connections we are starting. Three-phase transformer connections. Three-phase transformer connections. So mainly in three-phase connections, we have four types, mainly four, and specially we have like some special connections like delta zigzag, star zigzag, open delta, and Scott connection. So that we will see in the next after completion of this. First, we will see only these four. One is delta delta, first one. Second, star star connection, primary star, secondary star, and third, delta star, and fourth one is star delta. Total four connections we have. Combination of that star and delta, primary side and secondary side. Total four connections. Now, first, tell me one important point. Out of these four connections, which is the most important and most popular connection? Tell me. Out of these one, two, three, four, which one is the most popular connection? Okay. Okay. Enough. Enough. So most of you given right. Good. And some of you giving fourth one, star delta, but answer for this is delta star. Delta star is the most popular connection, because whatever supply you are getting to your home, that is from delta star only. So whatever we are using distribution, all transformers are delta star only, and star delta we use in transmission side. Transmission side only we use star delta, and delta star we are using mostly in transmission. Also we use delta star, but delta star we use in transmission side and also in distribution side. For distribution particularly, delta star only suitable, because secondary side when there is a star, neutral available, and due to that neutral you can connect single phase loads also here. But if it is star delta, secondary side you cannot connect single phase load, only three phase load you can connect. Okay, delta star is most popular connection. Now, what is the importance to know about this connection first? Why? One important thing we should know in all these connections is voltage relation. Now, for that we will consider primary having same turns, primary and secondary both will have same turns. Generally, tell me one point. If primary turns are 100, secondary turns are 100, then primary voltage, secondary voltage, same or not? Yes, same. Same turn, same voltages. But in these transformers, out of these four, in the third one and fourth one mainly, for same number of turns also, you will get different voltages. If you apply primary some 100 volts, secondary side you will get more than 100 volts in third connection. But in fourth connection, if you apply primary 100, secondary voltage will be less than 100. So it will give low voltage on secondary for same turns also. But first and second will give same turns, same voltages. So that is voltage relations we should know first. If you apply this much voltage, how much voltage this connection will give at the output? That relations we will see first. At the same time, in all these four connections, we have different vector groups. We have different vector groups, also called phasor groups. Different vector groups. Like in delta delta, we have two groups. One is 0 degree connection, and the second 180-degree vector group. 0 degree group, 180-degree group, or 0 degree connection, 180-degree connection we call. In the same way, star star also having same 0 degree, 180 degrees. In delta star, we have total four vector groups. Four. They are 30-degree lagging. In both the same it is. In these both the same four vector groups we have 30-degree leading connection, 150-degree connection, 210-degree connection. Total four connections we have. In these two connections, delta star four connections, star delta also same four connections. Okay, this is in angles, or we call degree connections. But in terms of clock, same connections we represent as clock. So in a clock, first of all, how many in a clock? How many digits are there total? 12. Very well known. Then in a clock, mainly we have total 12 digits anyhow. And what is the total mechanical angle here? 360 degrees. Okay, total 360 degrees. Now, what is the angle made by each digit? 30 degrees. Total 360 divided by 12. Each digit angle is 30 degrees. So there are two hands mainly in the clock. Two hands. What are that? Minute hand and hour hand. Don't say three hands. Three hands are there. That is one more is what? Second hand. Second hand we are not considering. Mainly two hands. One is minute hand. One is hour hand. So which hand is generally long one? Which hand is bigger? Minute or minute hand? Let this is minute hand, long one, and this is short hand or hour hand. This is hour hand. This is minute hand. Okay, this is minute. The long one is minute hand, and this is short one is hour hand. Now, what is the time it looks? What is this time in the clock? 1 o'clock. This is 1 o'clock connection. And in our three-phase connections, we will consider that this minute hand as a HV phasor. So you will understand once one connection is completed, you will understand. Just brief introduction I'm giving. This minute hand is representing as a high voltage phasor, and this short hand or R hand is representing as a LV phasor, low voltage phasors. In all our connections, we are considering HV is on primary side, high voltage winding is on primary side, low voltage winding is on secondary side. Okay, HV, high voltage we consider on primary, low voltage we consider on secondary for all connections. Now accordingly we draw the clocks. There you will get some angles or clocks. 1 o'clock, 5 o'clock. See, 0 degree means 12 o'clock connection. 0 degree means 12 o'clock, and 180 degree means how much? 6 o'clock. Like that, 30 degree lagging means 1 o'clock connection, and 30 degree leading is With respect to 12 is reference. 30-degree lag is 1. 30-degree lead is 11 o'clock. 150-degree lagging it is, but we don't mention. 150-degree means 5 o'clock. And 210-degree means 7 o'clock. So these are the clock connections totally we have in three-phase transformers. 1 o'clock, 5 o'clock, 7 o'clock, 6 o'clock, 1, 5, 6, 7, 11, 12. Okay, these are the clock connections we have. Now, what is the importance of this clock connection? Why we should know about this? Very important it is. Why we should know about these vector groups? Why? The main thing to know about these vector groups is for parallel operation of transformers. That's it. There is no other use of these vector groups. There is no other use. Only the main reason we are knowing about these vector groups is for parallel operation of transformers. Now I will show you the nameplate detail of one of the three-phase transformer. Then you will understand what is the need of these vector groups. Without this vector group on the nameplate, no one will sell the transformers, or no manufacturing company will sell or design transformers. Okay, observe that nameplate once. Let's see the nameplate once. See this. Observe this. So this is a nameplate of a three-phase distribution transformer. Okay. Now here on the nameplate, you can see the first topmost, we have kVA rating of transformer. kVA rating of transformer. It is a 16 kVA transformer, and voltage at no load, or the rating, voltage rating of transformer is there 11 kV by 433 volts. 11 kV by 433 volts. Okay. High voltage is 11 kV, low voltage is 433. So from this low voltage, you are getting supply, single phase loads, single phase 220, 230 around that. And three phase means this 430 volts will apply. And there is BIL. BIL means basic insulation level of transformer, because we are facing some insulating material between high voltage and low voltage windings. So that basic insulation level used is 75 kilovolts peak. Okay. And this is current rating. What current? You can find rated current. How to find rated current? What is the formula to find rated current? I equal to kVA rating by root 3 into line voltage, any side, primary side, secondary side. So if you find the primary current, kVA is 16 kVA divided by root 3 into 11 kV, the high voltage current you will get 0.84 amperes. And secondary rated current, same formula, if we use, you will get secondary side this 21.33. Check if you want it is. Check if you want the current using this relation, you will get same answers. So these are the rated current of primary and rated current of secondary winding, and frequency given 50 hertz. And now there is a vector group. This is important. Vector group. This transformer belongs to which vector group? The vector group of this transformer is DYN11. So actually N no need to mention, but they are given still. What is DY means what? DY indicates delta star connection. So always primary letter is capital. High voltage winding we indicate with capital, and low voltage winding we indicate with small. DY N. So N is neutral, that is anyhow no need to write. DY11 is enough. So this transformer belongs to which vector group? 11 o'clock connection it is, or 30-degree leading connection it is. So what that means? So that we will see what it is. 30-degree lagging or leading, what they are. These are the angle between what, so that we will observe in our connections. So this is the vector group of this transformer. So here DY11 means all transformers in the distribution will be DY11 only. All are DY11 only. So you have to manufacture always same type of vector group. If you manufacture some other DY1, and if you bring that transformer to operate in parallel with the already existing transformer, then there is a problem of circulating currents in parallel operation. So I will show you in parallel operation what is the problem of different vector groups. All transformers should have same vector group to operate perfectly in parallel operation. Otherwise, circulating current will get, and it may damage windings. So this is the importance of this vector group in three-phase transformer. Definitely it should mention. Okay. And there is next impedance or percentage impedance, that is percentage impedance of transformer given as 4.5%. So if you remember, what is the maximum regulation of a transformer? Percentage impedance itself. So in this transformer, the maximum voltage drop is this 4.5%. How much voltage will drop? 4.5% only will drop, maximum. Okay, that is 4.5. Next, energy efficiency level. So we have three levels we have. Third level is energy efficiency is very good. So like that, it is moderate level, it is this type of transformer. Now, second, maximum total losses at 50% rated load. Maximum total loss at 50% rated load means if you operate this transformer at half means how much? 8 kVA. Full load is 16 kVA. Half means 8 kVA. So at that time, the total loss is 135 watts. Total loss at 50% load. Now, see, next one, Total losses at 100% rated load. 100% means full load condition. Under full load, this is the copper loss. This is the total loss, 440 watts. Total loss in this transformer is 440. Now, next one we have type of cooling. Type of cooling, ONAN means oil natural, air natural. So this is mostly all distribution transformers will use this type of cooling only. Oil natural, air natural. Oil means oil will be there inside. Transformer oil providing cooling, and air, that air will touch the radiator tubes and provides cooling to transformer. That is natural. Oil natural, air natural cooling. Okay. Next, temperature rise over 50 degrees centigrade. See, above 50 degrees, how much temperature rise for oil and winding separately they given. Oil temperature rise is 35 degrees centigrade and winding temperature rise is 40 degrees centigrade. Now, what is the total temperature here? 75 degrees centigrade. So, maximum this transformer is allowed to operate up to 75 only. Okay. Next, mass of oil. Weight of oil given 88 kgs. Volume of oil is 110 liters. Total weight of transformer is 318 kgs. So the main thing in this is this vector group, KVA rating, voltage rating, and impedance. So these are the important things for us. Okay. Mostly all transformers will be DY11 only. Uh, No, basic insulation level given for, no, it is not mentioned for LV, but it will be common for both because insulation where we place commonly between high voltage and low voltage winding. No, so commonly it is given, not separately for both. Okay. That is approximately 440 watts because that is not only copper loss. No, both iron and copper loss both are there in that. Then how can you multiply both directly 4 times? Yes, total loss means both the losses. Air natural, oil natural means you are not providing additionally any cooling there. Naturally air is there, naturally oil is there in transformer. That's it. They are always present. No, separately you are not providing any cooling. That's why we call natural, natural, oil natural, air natural. BIL means basic insulation level used in transformer. So this is a phasor diagram means what is this here? This is a star connection. It is, this is star connection and this is delta connection. So they given UVW primary side 1U, 1V, 1V, 1W means what? Actually, it is primary terminals, primary high voltage. Actually, we are taking ABC, three phases. Like that, they taken UVW, or somewhere you may see RYB also. Okay, any notation. Primary side, secondary side, neutral secondary side. Okay, this is primary delta, secondary star. Just connection they made like this. Okay. Yes, that 11 kV and 433 are line voltages always. Impedance means voltage drop, not loss. Impedance. Due to impedance, we have voltage drop. In voltage regulation, we have seen. Yes, 11 means leading. Yes, for neutral also bushing is required. DY11 means delta star neutral 11 o'clock connection. DY11 connection it is. What it is, what it means, we will see now. We will see that now. Yes, percentage Z means voltage regulation. We have seen the voltage regulation, maximum voltage regulation, how much percentage Z only. So they indicated here how much drop maximum in this transformer. Energy efficiency level, we have three types. So this is second level. So that you will get not required here. That is not important. In three-phase transformer, we always keep primary as HV. So that is not necessary. But most of the distribution transformer primary HV only, no? Primary HV only for all distribution transformers. Secondary LV. Why? What is the voltage you are consuming? What voltage required to your home? High voltage or low voltage? Low voltage. That's why secondary is low voltage. All loads are lagging. Then what? Actual 50 degrees means generally it maintain. Ambient temperature means at any cost, mostly the temperature of the transformer will be around 50 degrees centigrade, because outside temperature itself in normal days 30, 35, and during summer nearly 40, 45, and 50 degrees will be there. Above that, how much will rise? That is, yeah, that may be core or shell type. Core or shell type. What? Akash. If I buy it, then there will be my name on customer blank. Yes, very good. Life of transformers is generally high, so 5 years. That depends on its working and load on the transformer, because generally life will be more than 5 years. 5 to 10 years will be there for every transformer, but in between if it damaged, the reason is load. Who should take care transformer? You only should take care. You means like electricity people. Electricity department should take care of the transformer. How? They should arrange the load on the transformer like that. Suppose if load consumers increase, then if they keep the same transformer at the same place to supply heavy load, transformer will damage. That people should take care of that. If load is high, they should keep a big transformer or two transformers in place of one transformer. Okay. Voltage drop. Voltage drop is whatever EMF induced in that, some voltage will drop while coming to load. And loss is what? Loss is in the form of heat. Voltage drop concept is different, loss is different. So triangle in the bottom, this is phasor. So you no need here. I will show you now. DY11. So I will show you that triangles now. So you no need to consider, because now itself we don't know about this. We will see now that vector groups. See, doubts will come now very quickly. So before completing the concept itself. 35-year-old transformer. Yes, maybe it will be there. If you are protecting well the transformer, they will give huge life. In general, 5 to 10 years, if you buy a new transformer, mostly without damage, you will get. But after that, problems will come, and if you rectify that, still you can use the transformer for 10 more years. Okay. Why losses at 50%? So they mentioned at half full load when you operate, how much loss? Okay, these are all not important for us. Only this left hand side important. Oh, you forget about right side. Okay, let's start the first connection now. First one is delta delta. Yes, electricity board will charge whatever losses they are occurring, they are getting. So they will place that losses cost everything on the consumers itself. Okay, 1960, very, very good. Yes, they can use because if you see ceiling fans also from our old days, maybe from 30 years also that fan is working still. Yes, we can use that. Minimum life will be 5 to 10 without any fault if you properly take care. And after that, if you do service of that repairs, you can use for any number of years. Yes, very good. Yes, single phase transformer also same data, but voltage rating, current rating should be less. Now, right, the first one, delta delta connection. First, delta delta connection. So in delta delta, how many vector groups we have? Delta delta connection, we are using only two vector groups. What are the two vector groups? 0 degree and 180 degree. 0 degree vector group, 180 degree vector group. Only these two we are using in delta delta. If you got any other, just leave that. You may get some 8 o'clock connection. These are all we don't have. We have only six vector groups. Six. So generally six vector groups in that 0 degree, or in terms of clock, if you say 12 o'clock, 1 o'clock, 5 o'clock, 6 o'clock, 7 o'clock, and 11 o'clock. Total six vector groups we have. That's it. And if you got in some other 8 o'clock or 4 o'clock like that, just leave that vector groups. We are not using according to our Indian standards. They are only these six vector groups we are following. But manufacturing will be mostly one vector group. One vector group only, mostly they manufacture, because whatever distribution transformers or transformers we are connecting in parallel outside, all should have same vector group. Otherwise it is difficult to operate in parallel. Okay, so what happens, we will see there in parallel operation. Let's see first. In delta delta, two groups, 0 and 180. So let's see the first connection. First one in this. So listen carefully, first connection, so that the next connections becomes easy to you. Listen carefully first. So first draw the three phases of primary and secondary. First, primary three phases. A, B, C I am taking primary. A, B, C. Three phases I am taking first. These are three phases: A phase, B phase, C phase. Similarly, secondary side, small a, three phases on primary, secondary. Okay. Now, first indicate the names for this. So I'm considering A, B, C indications. A, B, C. So phase A, primary, secondary. Phase B, primary, secondary. So secondary side, we always consider small letters. These are all our Indian standards. According to standard, we are following same. And don't say that I will use small letters on primary and capital letters on second. You can use the same connection you will get, but where is the standard you are following? What is the need of that standards we need to follow? What is the need to follow some standard? If you follow standard, suppose you placed a manufacturing company of a transformer. Okay, when you place a manufacturing company of a transformer, what type of transformer you will construct or design? Whatever you want, you will design yourself. If you design yourself, no one will buy from you, because that is not having any standard. And because if they buy any transformer, no customer suppose, then they need to operate that transformer in parallel with existing transformers. Already some transformers are working, you need to place one more new transformer there. Then if you don't have any standard of the transformer, if you directly place, it will damage other transformers, and also your transformer will damage. So some standard required to construct any transformer, manufacturing also, anything. Based on the standard only, they will design everything, transformers, machines, motors, generators, everything that is. Okay. For that, we are following same standard. Primary side capital letters indication, secondary small letters. Okay. Now, after taking three phases, the next step is polarity test. So conduct polarity test individually for each phase. Phase A, phase B, phase C. Polarity test. So mark the polarities. Suppose I got polarities like this. Polarities are marked by conducting polarity test. Okay. Second step it is. First step, take three phases and then conduct polarity test. Now assign terminal names. Terminal names like this. So primary side A phase having two terminals. This is A1, this is A2. And can you take A1 here, A2 here? No. Why? Wherever dotted terminal is there, indicate that is with suffix 2, even A2 it is. Wherever dot used there, dot. Similarly, B1, C1, B2, C2. Okay. Similarly on other side, A1, B1, C1, A2, B2, C2. Now, this is the next step, indication of terminals. Next step is connection. What is the connection we are using? Primary delta, primary, this is input, supply we give to these terminals, and this is output terminals. Load is connected to these three terminals. This is primary, this is secondary, input output terminals. Now let us join the three phases such that it is a delta connection. How to connect a delta? While connecting delta, you should connect opposite polarities or not? Yes, means A1 should be B2 connected. Like that we have to join. A1 is connected to B2. B1 is connected to C2. C1 is connected to A2. Or in this way also you can connect A2 with B1, B2 with C1. Like this also you can connect. But opposite. Dot with undot. Dot with undot. This is a delta. Now these three wires we will take outside. Why outside? You should give source or not? Supply. So these are the three terminals where we are giving supply or input. These are called input terminals. This is input side. Here we give supply to the primary side. Next, similarly secondary side, A1, B2, B1, C2, C1, A2. And again three terminals taken outside. Why? Secondary side what we connect? Load. So this is output terminals or load terminals. Clear up to this? Input on, that is source, supply given to primary terminals or input terminals, and load is connected on secondary terminals. Now this is a delta delta connection. So we got delta delta, but we should know what type of vector group it is. Is it a 0-degree vector group or 180-degree vector group? Which one it is? Remember, delta delta and star star, these two connections. Just by observing figure, you can directly tell this is what type of vector group. So this is a 0-degree vector group. 0-degree connection it is. Or 12 o'clock connection it is. Directly I can tell. Star star also you can tell directly. But remaining third connection and fourth connection, we cannot tell directly. We should draw complete vector group, complete vector analysis. Finally, you can tell which type of vector group that is. Delta delta, star star, easy to tell. Now, which connection it is? 0. So before going to that 0-degree connection, let's see what are the voltage relations here first. Voltages means if you apply a voltage, input voltage V1 primary side, how much voltage you will get on secondary side? That depends on number of turns. So that voltage relation we have to know. Whatever we will proceed in the first connection, same as it is for up to last connection. Okay, same as it is. Listen this carefully. See, make a note beside this diagram. Make a note here. Considering primary turns, what is N2 by N1 generally we call? Transformation ratio, N2 by N1. And what is N1 by N2 we call? Turns ratio. So let us consider N1 by N2 is the phase turns ratio of three-phase transformer. Turns ratio. So this turns ratio, I am considering some variable x. Some variable x. X means turns ratio here. Here x means turns ratio. What is K? Transformation ratio. N2 by N1. But I am considering N1 by N2 as x. Okay. Now we know E2 phase by E1 phase. What is this? N2 phase by N1 phase. Okay. Both equal now. Now can I write this is as 1 by x? Yes. N1 by N2 is x. Then N2 by N1 is 1 by x. Therefore, what is the secondary phase voltage? Is equal to primary phase voltage divided by x. Secondary phase voltage is primary phase voltage divided by x. Clear? Secondary phase voltage, primary phase voltage by x. Remember this. Same equation we are applying now for all connections. Remember this equation. Now observe the figure. Let the primary voltage given at the input side. This is what line voltage V1. Line means what? Between two terminals. Whatever we give, that is a line voltage, line to line. Phase voltage means line to neutral. But anyhow, here we don't have neutral. This is line voltage. And what is phase voltage in delta? In delta, line voltage equal to phase voltage. Both are same. Okay. So V1 is line voltage. And what is the phase voltage? Same. Phase voltage means voltage across each phase. This is same V1 only. Okay. V1 only, that is. This is our primary phase voltage V1. Then what is the secondary phase voltage here? Tell me now using this relation. Secondary phase voltage equal to primary phase voltage by x. So consider x is to 1 is the turns ratio. If primary phase voltage is V1, what is secondary phase voltage? V1 by x. How? Using this relation. I applied this equation. Secondary phase voltage is primary phase voltage by x, where x is what? N1 by N2. This one. Okay. This is secondary phase voltage. Now tell me what is the line voltage on secondary? Secondary also delta. So line voltage is equal to phase voltage. So this is V1 by x. So finally, if you apply a voltage V1, line voltage, primary side, how much voltage you got on secondary? V1 by x you got. Clear? You applied 400 volts. How much voltage this connection is giving at output side? 400 by x. X means turns ratio. So they will give in the question turns ratio is 0.5. What is the secondary voltage? Or turns ratio 1.5. What is the secondary voltage? Easily you can find using this. Now we are comparing x equal to 1. Let x equal to 1. X equal to 1 means what is N1 by N2 equal to 1. N1 by N2 equal to 1 means both are same turns. Primary side 100 turns, secondary side also 100 turns, for example. Then what is the primary voltage, secondary voltage? Both are same. Whatever you applied, same voltage it is giving. Same voltage. So let x equal to 1. Then if primary voltage is V1, secondary also x equal to 1, no? So V1. Same voltage. This is we call 1:1 transformer. 1:1 transformer. What is the other name of this 1:1? This is also called isolation transformer. Isolation transformer. What is the need of this isolation transformer? Tell me. Or 1:1 transformer. Generally, the main purpose is what? Either to step up the voltage, step down the voltage. And some cases we use 1:1 transformer. What is the use of 1:1? 1:1. Suppose I am considering single phase transformer. Observe here. Primary, secondary having same number of turns. Primary and secondary having same turns. If it is 100 volts, what is the voltage on secondary? Same, 100 only. Then we will give supply to this winding 100 and you will get 100 volts on secondary side. Then load is connected. Then what is the need of the transformer? Why can't you give directly from source to load directly without transformer like this? Then also 100 volts you are getting. Then what is the use of that 1:1 transformer? What is the use? For the load you are getting 100 by using this transformer, 1:1 transformer, same turns. Then why? What is the need of the transformer? Why should we cannot give directly that 100-volt source to load? Yes, there is a good reason here. That is isolation or 1:1. What is the need of that isolation transformer? Is this transformer will isolate the source and load. It will isolate. How? By connecting same number of turns. Then what is the use of this? There is a good use, that is load. Load side, many times faults will take place. Load side fault. What fault in your home? Tell me. Suppose in your home suddenly some short circuit takes place. Why short circuit? Due to some internal wiring problem. Phase neutral gets shorted or phase gets started if it is three-phase voltages. Or in your home some appliances got problem and short circuit takes place. Now, if there is any fault, if there is any short circuit fault here, if taking both the cases, this is transformer case, this is direct source case. If there is any short circuit on load, short circuit, then if you directly connect a source to load, whenever there is a problem at the load, and if there is any sudden short circuit fault, the source also will damage or not? Yes, because due to that sudden short circuit fault, very high current will flow through this source or generator. Directly that generator will damage. But when there is isolating transformer, if there is any sudden short circuit fault occurred, because of that high current, this winding will damage first. Once this winding is burned, it will isolate the source directly. Source will not damage. Source is safe. That is called isolating. So transformers are very important here. Between source and load, transformers are playing very important role. If there is no transformer, source may damage. But due to transformer, it is isolating. That's why at some of the places for protection purpose of generators, we use this 1:1 transformers, isolation transformers. Okay. Yes, impedance matching. 1:1 impedance matching also we use 1:1 transformers. Good. Yes, good. Okay. So we are comparing just in our example here, we are comparing with x equal to 1. Like this, we compare for all connections so that you will get one idea which transformer will give higher voltage on secondary, which transformer will give least voltage on secondary. This data you will get. For that reason, we assumed x equal to 1. For that delta we got, it is like 1:1. Star also will get 1:1. Okay. Now let's see what type of vector group it is. Completed this one, all of you? Taken it is? Yes, sir. Yes, fuse protection will be there. Let's see what type of connection it is. So I said it is directly 0-degree connection. So how it is, I will tell after completion of this vector group. Now observe, to find vector group, the procedure is primary side vectors, A phase, B phase, C phase vector, you draw directly first. Primary side vectors directly you can draw for any connection, not only delta, anything that is primary delta here. So draw primary delta. So I'm considering, let this is primary phase A. Primary phase A, it is A2 here, A1 here, and this is A phase. Okay, A phase two terminals, A1, A2. So that A2, A1 I taken. Anywhere you can take, not only like this, you draw like this also first, or like this also, or like this also, or like this also. So anywhere you can consider this, any direction. But in order to get a proper delta, I started like this. This is A phase. Next, B phase I have to draw. But before drawing B phase, check one time figure. See, B I have to draw. Before that, observe A1 is connected with B2. These two are joined. These two are same points. A1, B2, same points. So this is A1. So start from here and draw B phase. This is B2. A1, B2, same point. This is B2. So I am drawing in this direction. This is B2. This is B1. Terminals. B phase it is. Why not like this? Why not like this? You can draw like this also. But there is a proper sequence we have to follow. Always follow in the clockwise direction. You should get A, B, C sequence. Same sequence we follow for all connections, positive sequence. So A, B, C, like that we complete the complete vectors. All three vectors we complete like this clockwise. So if you draw A here, don't go like this. And if you go like this, it is going in anti-clockwise direction. A, B, and then C will get like this. A, B, C. That's why I'm not going in that direction. Clockwise I am moving A, then B, and B1 is connected with, observe, B1, C2 are joined here. B1 is connected with C2. So B1 connected with C2. Complete this delta. Like delta you should get C2, C1, C phase. So primary delta we have drawn. Okay. Suppose if it is star, you can draw like A phase. I taken reference here. This is A1, A2. Okay. Then B phase. From where we have to start B phase? So where which terminals we will short in star connection? Similar A1, B1, C1 only we short. Then B1 here, draw 120 degrees with the 120 degrees star connection like this. So like this we draw for star. So anyhow we will see in the next connection, that is okay. Primary delta is completed. Now the important here is drawing secondary delta. Listen, secondary delta we have to draw. So how to draw secondary phasors is, always for every connection draw the secondary phasors parallel to primary phasors. Suppose secondary phase A, draw parallel to primary phase A. So secondary phase A I am drawing exactly parallel to this. Okay, small a it is. Small a. Now can you put the terminals wherever you want? A1, A2? No. You should put that A1, A2 again. That A1, A2 should coincide with this primary A1, A2. Okay. Then where is A1 here? At this, A1 is this, A2 will be this. Okay. A phase is drawn exactly parallel to primary A phase. And A1, A2 also coincide. That should be there. Both should be in phase. Next, B phase. Now observe A1 joined with B2. Okay, A1 joined with B2. So start from A1. This is B2. This is B2, and draw parallel to primary B phase. Small b, capital V should be parallel, and both should be coincide again. So which one we got here? B2. Now this one B1. Check one time. B1, B2 inside or coincide or not? Yes, B1, B1, capital B1, small b1, capital B2, small b2 coincide each other. So this is right. And one more is there. B1 is there over. Next C2, C1. B1 connected with C2. B1 connected with C2. This is C2. Draw exactly parallel to primary. C2, C1, C phase. Okay. So anyhow here directly we are getting no problem. For delta star and star delta we need to take care. The two are the difficult connections. Delta delta star star easy connections on easily we can draw. Primary delta we have drawn and secondary delta also we have drawn. Now which connection? Still we cannot say here. Still there is some more to be built in this. That is, if you take a clock, suppose let us consider a clock. Tell me, in a clock we have two pointers, shorthand or hour hand and minute hand. How that pointers are rotating? That pointers are rotating with a base of center point or not? With a base, like from the center of this circle, the pointers are rotating. Pointers are rotating. Now these pointers are similar to a star connected phasors or delta connected phasors. See, star connection means like this, having a center point or neutral point, and the phasors are rotating. Now, which phasors similar to pointers of a clock? Delta or star? Definitely star only, because in star only we have the center on neutral point, they are rotating with respect to this. But in delta, we don't have like that. Okay. So in every connection, wherever we have delta, you should convert that delta into star. Means internally we draw a reference star connection. Internally, within this delta, we will draw a reference star. Okay, like this. See, internally, whenever there is a delta, only then we draw internal star like this. Internally, a star phasor I am drawing. Similarly, for this one also, I will draw a star phasor. Okay. Now I need to mark internally which one are the ABC. That is important. Which one are the ABC? For that, you should go previous figure. Observe input side or primary side. Which terminals are coming outside? See, some wires you are taking outside to give supply. Which are coming outside? A to B to C2. A to B to C2 are the outcome terminals. Okay. A to B to C2 are the outcome terminals. Now, secondary side, which are the outcome terminals? Outcome terminals means whatever the whites will come outside, they are called outcome terminals. Which are outside here? A to B to C2, small a to B to C2. So remember, A to B to C2. Similarly, on secondary also we have same A to B to C2. First, just circle that, because whatever you circle A2, corresponding phase in the star is phase A. For that marking only we are circling that A to B to C2, and similarly here B phase and C phase. Otherwise, which one is ABC inside, that is difficult to find. For that reason, just circle and mark. And here also A2 is this, so A phase it is, this is B phase, this is C phase. Now let us take any one phase in the star connections. Star connection is the reference, not actual. Delta only actual, but for our clock connection we consider that internal star. Now I'm considering capital A is reference. Capital A I'm taking. Now if you take capital A in a clock, same capital A, just move in a clock, just move in a clock. So this is capital A. Okay, it is pointing toward. Now secondary star you take outside and overlap on primary side. Take this secondary star outside, just imagine, take it outside as it is and place exactly with both neutrals coincide. Then capital A small a exactly in same line or not? Yes, that is called both are in phase. Now small a also you will get exactly in phase. Small a, small hand, that is shorthand, small a. Like that you can take any phase. B phase also you can take, C phase also you can take. Angle is how much, first tell me? Both are in phase. So angle is 0 degree. So this is called 0 degree connection. 0 degree connection. Now what is the time it looks? In a clock, what is this time? In a clock, what is the time? 12 o'clock. This is called, in terms of clock, 12 o'clock connection. Okay. Or simply we represent in terms of directly transformer connection, DD0 or DD12 connection it is. Primary capital letter delta, secondary delta, so small d, that is capital D, small d, 0 degree connection, or we also call DD12 connection it is. Both are same, DD0 or DD12. Okay, like this we indicate. You can take B also, but if you take B, what is the problem is, observe, B is pointing 4, small b also pointing 4, then both in phase, angle is same, 0 only, but is it a proper clock here? Tell me, is it a proper clock? It is a 4:20, 4 hours 20 minutes. Is it a proper clock? No. Clock means we need exactly actual, like 1 o'clock, 11, 12, like that we require. For that reason, A we taken. Why A? Because A already pointing 12. That's why directly A we are taking. Okay. Otherwise, if you take B, what you have to do is you rotate this capital B such that it is pointing this 12. Then you will get 12 o'clock only anyhow. Okay. So people will get doubt why A phase only taken, why not B phase or C phase. Any phase you take, angle is same, you will get. But to say a proper clock, it should point 12. That's why I taken A phase. Clear all of you this? Clear? Yes. Capital D, HV, high voltage are primary side capital letters. So internal star we are drawing for clock connection only, because direct delta you cannot compare in a clock. Direct delta phasors are not similar to clock pointers. That's why we take an internal star. How to directly draw internal star in delta? Then internal phasors we need to mark A, B, C. To marking that vertices we need to consider first. Vertices how we are getting from the connections. In primary, which terminals you are getting outside A to B to C2. So that A to B to C2 I circled here. And secondary side, which terminals you are getting outside, small a to b to c2. So that is I circled here. And accordingly, internal ABC I marked, internal ABC. Then internal primary sides, secondary side I am comparing in a clock. Then I got 0 degree connection or 12 o'clock connection. So how to tell directly delta delta is very easy. It is observe primary terminals, secondary terminals. Both same terminals or not. Means A to B to C2 on primary, secondary also A to B to C2. So when they are same, that is a 0 degree connection. Suppose if they are different, primary side A to B to C2, but secondary side A1, B1, C1, then it is a 180 degree connection. Just by looking the diagram, you can tell connection. No need to draw these vectors. No need to draw this. Directly you can tell. Okay. So after listening one more connection, still clarity you will get how to draw these vectors. First complete up to this. Yes, anywhere you can give input A1, A2, A3, not A1, A2, A3, A1, B1, C1. There also you can give input. After listening second connection, still you will understand clearly. See the second connection. Second connection in delta delta. Second connection in delta delta. All of you completed this diagram. So listen carefully up to third connection, delta star. See, delta delta, I will tell two connections. Star star also I will give two connections to you. And delta star also I will give four connections completely. But star delta, mostly I don't give the four connections. You should do your own that fourth one, star delta. Okay, first listen these three connections properly. I'm leaving that fourth one almost to you only. So let's see you are able to do the fourth connection or not. Okay, so you will get good clarity up to third connection. Fourth connection, if you able to do, You got completely that is. Okay. All of you completed this. For any transformer, not distribution or power transformer, anything, same procedure. DD0 is what? Delta delta 0 degree connection or delta delta 12 o'clock connection. Anything we can call. See the second connection. Second connection in delta delta. One connection in delta delta is 0 degree. Second is 180 degree. So that 180 degree, how I will show you here. See, for this second connection, I am not changing primary side. See, this primary side delta I don't change. Same as it is, I will keep. So draw the figure quickly. Primary side I am not changing any connection. I will keep same as it is. A, B, C. Same as it is. And same connection I will do. So first I will draw completely. Secondary side, three phases. Small a, small b, small c. And conduct polarity test. Dots here. Polarities are marked in each phase. So these are all same procedure, same story for every connection. Okay. Every connection, same story up to the connection you made. A1, A2, B1, B2, C1, C2, A1, A2. So no need to tell every time, you need to draw your own it is. Next step, primary delta, no. So primary I'm not changing, same as it is like previous I'm doing A1, B2, B1, C2, C1, A2. Okay. Now secondary side. Previously I joined A1, B2, but now I will join like this, A2, B1. This is also delta. This is also a delta only. Like this also you connect. Now I will take A1, B1, C1 outside here. Okay. See, source is connected across A2, B2, C2. This is source terminals, and load is here A1, B1, C1. Anywhere you can connect source, anywhere you can connect load, anywhere. That is one connection. This is one connection. Now here you will get a 180-degree connection. See what it is, how it is. Observe. First again it is voltages are same. Voltages are same. See, if you apply primary voltage V1 here, X is to 1 is the turns ratio. How much voltage you will get on secondary? Same as it is previous connection, V1 by X. No changes in any voltages. Same only. Voltages no change, but the vector group will change. Angle will change between this primary line voltage and secondary line voltage. This angle we are considering here. That's it. Now see the connection, what type it is. So drawn it is all of you. Going to next page. See this primary delta, no change. So I'm drawing same as it is this primary delta. I did not change primary connection. So same as it is, you will get A2, A1, A phase, B2, B1, B phase, C2, C1, C phase. Okay. Primary delta, no change. So terminals also same, A2, B2, C2. First draw secondary delta, no. Secondary delta. Now again draw A1, A2. A phase, secondary A phase parallel to this A1, A2. Okay, parallelly drawn. Secondary A in phase, exactly in phase with the primary phase A. Next, before drawing B phase, you need to observe the figure first. Observe the figure, B phase. In A1, A2, A2 is connected with B1. A2, terminal A2 is connected with terminal B1. Okay, A2 connected with B1. Where is A2 here? A2 is connected with B1. So this point is B1. Now in which direction we have to draw B phase? Right side or left side? Right or left? Anywhere B phase is parallel only you will get. But you should draw towards right side. A2 is B1. This will be B2. Now let us check one time. This B, small b and capital B both in phase or not. See, B1 coincide. When you in place in phase both B1 coincide and B2 will coincide. So this is correct. But if you draw towards left, then if it is B1, B2 is here. Then if you place as it is both inside, they did not coincide each other. Both should be coincide in same line. B1, B2. So this is right. Clockwise you should get. The other way is you should remember clockwise you should get ABC. Right? Next. B2. This is B2. B2 is connected with C1. B2 joined with C1. So B2 is this, C1 is here. Then other only the thing is the directly here, C1, C2. C phase parallel, both coincides. The secondary delta we got. Okay. Now draw the internal star for clock connections. Which one are the outcome terminals on secondary? A1, B1, C1. Circle that. A1, B1, C1. Now draw internal stars. Internal star. Here also internal star. Internal star phasors are only for clock representation we are taking. Actually delta only that is. Now take a clock. Now which one are the A, B, C in the primary set? Same. A, this is B, this is C. Secondary set, this is A1. So this is A phase. This is B phase. This is C phase. Okay. Now take a clock. Taking A phase reference always. So A is coming exactly pointing towards 12. This is capital A. Pointing 12 it is. Now let us take the secondary star overlap on primary star such that both the neutrals coincide. Let's coincide both star neutrals. Then check capital A and small a. Small a you will get exactly opposite. So small a you will get exactly opposite. Small a it is. Okay. Now it is pointing 6. So what is the angle between this primary HV phasor and LV phasor? HV means capital letter. LV means small letter. What is the angle between these two? 180 degrees. 180 degree connection. Or what is the time it looks from the clock directly? 6 o'clock connection. And how to represent this connection shortly? DD6 connection it is. Delta 6 o'clock. Okay. Clear all of you? Okay. Kushal, current should leave from dot in secondary. So in these connections, you cannot observe that current entering, current leaving. Do you know that current enters at dot here? Source, three phase. The three phase currents are 120-degree displacement. Then how can you say this current is entering or this current is entering? One may enter, one may leave, or like that. That depends on magnitude of variation of current. No? If you take a three-phase signal, how the three-phase signal? 120-degree displacement. So if it is R phase, okay, Y phase is again 120-degree displacement. Three-phase currents. B phase again 120. So if you take at any instant, see at any instant, if you observe, is all the three will have same magnitude? Suppose take at 90 degree. R is having this positive peak, but remaining Y and B having some negative values, negative current. Negative current means that may be reverse. So don't apply that formula here. That is for single phase you can consider, or individually for each phase you can calculate, but not directly for three phase. Okay. Okay. So how to say this is 180-degree directly? Observe primary side A2, B2, C2. You have A2, B2, C2 are the outcome terminals, and primary side. Secondary side, what you have? A1, B1, C1. So they are different suffix, no? Different. A2, B2, C2 on primary, A1, B1, C1 on second. If they are different, this is a 180-degree connection. Okay. If they are same, see primary A2, B2, C2, secondary also A2, B2, C2. If they are same, that is 0-degree connection. Directly you can tell this connection. But for delta star, star delta, you cannot tell this type of directly. Okay. So after break we continue, because delta delta two connections are over, but still we need some features. What are the features of this delta delta? Some important points we will note down. So after that we go to next star star connection. Okay. Take break. right? Features of delta delta. Studying features. Features of delta delta transformer. So same as it is, we proceed for all other connections. First clock connections and then features of each connection. Features means relations, the important properties of this delta delta we will see here. Tell me first. uh, Suppose there is a delta delta transformer and star star transformer in front of you. So in front of you, one is, there is two transformers. One is delta delta, other is star star. Okay, two transformers are there. One connection is delta delta, one transformer, other is star star. Both having same voltage rating, 400 by 11 kV by 400, 11 kV by 400, same. Now, how can you identify this is a delta delta connection, this is a star star? Don't tell that I will check nameplate. So nameplate is not available. Only transformer core winding available, not tank also. I'm saying only transformer core winding available in two transformers, transformer core, transformer winding. Then how can you say this is a delta delta transformer, this is a star star transformer? How can you identify this? Very easy. Yes. Okay. Number of bushings. Okay. Number of bushings also not available. Number of bushings not available. Yes. Number of turns. Good. Number of turns. One way is number of turns. Suppose number of turns also not visible because it is covered totally with insulating material. Then only wire is visible. Wire. Then you have to check thickness of that wire. Thickness. One will be thick wire and other will be thin wire. Now, which transformer winding will have thick wire and which one is thin wire? Yes, we know. Generally, first tell with respect to delta delta and star star relation. In delta, what is the phase voltage? Equals to line voltage. But in star, what is the phase voltage? Line voltage by root 3 times. Suppose line voltage is same, I'm taking 11 kV. With respect to primary, I'm talking. Anyhow, secondary also same analysis. 11 kV primary side. If it is a delta connection, 11 kV is what? Line voltage. Then if it is a delta, what is the phase voltage in delta? Equal to line voltage, that is 11 kV. Both are same. But if it is a star connection, line voltage is 11 kV. Line voltage is same 11 kV. So both transformers same line voltage. Line voltage 11 kV. Now what is the phase voltage in that? 11 kV by root 3. Calculate, check how much. 11 k by root 3. 11 k by root 3. 6350. This is 6350 volts. Now observe. If it is a delta connected transformer, the phase voltage is 11 kV. If it is star connected transformer, the phase voltage is 6350 volts. Then which transformer required more number of turns per phase? In each phase, more turns. So this one required more number of turns, but this one required less number of turns per phase. So each phase is having less turns. Even that less turns, phase voltage 6350, but line voltage in star you are getting high. Root 3 times of this, no? Then 11 kV you will get line voltage. So for the same line voltage in delta delta and star star, which connection requires more number of turns? Delta required more number of turns, and star required less number of turns per phase. Like that. What is the phase current in case of delta? Line current by root 3. And in star, what is the phase current? Equals to line current. Generally, which values are high? Generally, line values. Line voltage or line current is higher. Now, if you take line current, suppose 20 ampere, for example, line current is 20. If it is a delta, what is the magnitude of phase current? Less, 20 by root 3. But if it is a star connection, what is the line current? Equals to phase current. Phase current equals to line current. That is, phase current is high current or not? Yes. Okay. Now, with respect to thickness of conductor, thickness of that copper wire we are using, delta delta required thin wire because current is less flowing in this, and star star required thick wire. Thick wire. Now easily you can identify. Suppose they given one wire from delta, one wire from star. Delta delta connection, star star connection. Just by observing thickness of the wire, you can say this is a delta transformer, this is a star star transformer. You no need to check anything. You no need to see number of turns. You no need to see any nameplate details, or no need to observe bushings. Nothing. Just by thickness of wire, you can say this is a delta delta. Little variation will be there, not so much. See, if you see from long distance, you cannot observe also. Only if you hold that mostly in the hand, then you can observe little variation in thickness of wire. That's it. That much very small variation will be there in the copper wire. There you can tell this is a delta delta, this is a star star. Okay, like that. If it is a delta delta transformer, what is the phase voltage here? Equals to line voltage. So as phase voltage is higher voltage, each phase required more number of turns. Okay, write the first point. Right, first point, as V phase equal to VL, this connection requires more number of turns, per phase, more number of turns per phase compared to star star, Okay, first point. Next, second point, this is also related to same phase voltage, line voltage. See, what is the phase voltage in delta? Equals to line voltage, both are same. So as phase voltage equals to line voltage, in delta, what is the, this is high voltage now, then what is the phase voltage? Is high voltage. Then what is the insulation requirement? So if you remember in the single phase transformer winding placement, LV, HV, insulation, LV, insulation, again HV, like that we are placing. So as phase voltage is high, then what is the insulation required to place in the core, or between winding and winding, or between core and winding? More amount of insulation required or not? Yes. High voltage is high insulation required. Low voltage, low insulation is enough. So here this delta delta required high amount of insulation compared to star star connection. Write that point. It requires more amount of insulation. Okay, it requires more amount of insulation. Next, third point. This is regarding current. As I phase equal to IL by root 3 na, in delta delta, IL by root 3, phase current is less. As phase current is less, then what is the thickness of wire required? Thin wire is enough, because high current, thick wire is required. Small current, thin wire is enough. Right. As I phase equal to IL by root 3, it requires a thin wire. Compared to star star. Thin wire compared to star star. Okay. Next point. Next. Completed. Next point. Fourth. Now this is regarding voltage relation. If you apply voltage V1, how much voltage magnitude you got on secondary? V1 by X we got. Okay, write that point. For an input voltage of V1, for an input voltage of V1, suppose some 400 volts example. For an input voltage of V1, this connection will produce will produce an output voltage of V1 for the when V1 when x equal to 1, that is for the same number of turns, for the same number of turns, for the same number of turns. Okay, x equal to 1, actually V1 by h there, now x equal to 1 we take same number of turns. Okay, clear? Next point. Now tell me, in this connection, what is the shape of EMF in the winding always? Sinusoidal or not? The shape of EMF in delta delta is dash sinusoidal. Why? I said any one side, either primary or secondary, if there is a delta, the EMF in that connection is sinusoidal directly. Here both side we have, so still better. EMF is sinusoidal always, right? The shape of EMF induced. The shape of EMF induced is sinusoidal. So which connection there is a problem? Only star star, because there is no closure path on both the sides for third harmonic current. That's why EMF is peaky wave. That is also with which type of core, or that is magnetic circuit, shell type only, it is peaky wave. If it is core type, 3-limb core type, there whatever the connection, EMF is sinusoidal. So that yesterday we have seen why it is. Okay, right. Shape of EMF induced is sinusoidal. Next point. Now, is it possible from delta delta to supply single phase loads? Is it possible to supply single phase? No. Only three phase load we can connect. Three phase load, but not single phase, because neutral is unavailable from delta. Only lines available, A, B, C, three lines. So you can connect a three phase load, but not single phase load. So write that. It is suitable for only three phase loads, or it is not suitable for single phase loads, because neutral is not available. For single phase, neutral is required. Okay, so these are the some features of this delta delta transformer. So in the same way we proceed for remaining connections also. Now let's see for second connection, star star. These two are simple. Delta delta, star star are easy to draw. Right, next connection, star star. Okay, thank you. Next one, second connection. First one is delta delta, second one is star star. In star star, how many connections are possible again? Same, two connections. Two connections are there. 0 degree to 180 degree, same as it is delta delta. So first of all, you are anonymous attendee. Then how can I tell everything to you? There is no name to you first year. So it is very difficult to read all your messages at a time, because there are so many messages near. Then at a time it is not possible. Now scrolling is becoming very difficult. So whatever is possible, I am reading. That's it. Okay. See, star star, two connections we have. Right, first one. First. Same procedure again. Take primary three phases. A phase, B phase, C phase. So you draw quickly because same story again, no need to tell every time. You draw quickly this. Take three phases, primary, secondaries, and conduct polarity test, and then join as a delta or star based on given connection. So we need star here. So we need to join like a star only. First, primary side A, B, C, secondary A, B, C. Follow same procedure whatever we followed for first one. Polarities, and somebody asked previously how polarities are marked. So everything I said, I given clearly in the first case itself. How we are marking polarity? You conduct polarity test for each phase first. Then only polarities are marked. Okay. Is it same? Is maybe you will get dot here or dot here, but I am arranging winding like that. Dots are on one side. Okay. A1, A2, B1, B2, C1, C2. Similarly on secondary A1, you should not change these terminals. Dotted terminal always even number only. Dotted. Don't ask why it is. This is one standard we need to follow. Why means standard. So this type of dots will come first. Up to this one, every connection is same. Now primary is star. So join like a star. So if you want a star connection, how to join the three phases? Join at a neutral with the same polarities. Anyone you can join. See, suppose I am shorting now A1, B1, C1. Or you can also short A2, B2, C2. Anywhere you can short. Any three you can connect as a neutral. So I will take A1, B1, C1. This is a neutral point. Okay. Similarly on secondary, let us take first A1, B1, C1. This is a neutral on secondary. Now primary side, we will apply source to these three terminals. Voltage will give to this supply source, and load is connected across these three terminals. Load is here. Now which connection? Tell me directly. 0 or 180? Already I said in delta. 0 or 180 it is. Yes. 0-degree connection. Why? Same outcome terminals. If it is same, 0. If it is different, 180. For delta delta star star, you can directly give this 0-degree or 180. Yes, right. Now let's see the voltage relation first. Just like delta, what are the voltages we are getting in this? So same I am considering x is to 1. What is x? N1 by N2 turns ratio. X is N1 by N2 turns ratio. So if I apply a voltage V1, line voltage V1 primary side, how much voltage I will get on secondary, I need to calculate. For that, what is the previous one equation we used? Secondary phase voltage is primary phase voltage by X. Use the same relation for all. Now, this is V1 line voltage, primary side. Then what is the phase voltage? Phase voltage, how much? Star connection it is. In star, phase voltage always line voltage by root 3. Okay. So line voltage we taken V1. So phase voltage will be V1 by root 3. Clear? Phase voltage I written. This is our primary phase voltage. Now what is the secondary side phase voltage here? How much? Using this equation. Primary phase voltage by X. So primary is V1 by root 3 divided by X. So totally it is V1 by X root 3 will come. Then what is the line voltage? Line voltage. Line voltage is what? Root 3 times of phase voltage. So root 3 times of this. Root 3 cancel. Finally, you will get V1 by X. So therefore, if you apply a voltage V1, how much voltage you are getting? V1 by X you will get. Output voltage. And if you take again X equal to 1, just like previous connection, If voltage V1 applied, output also V1. Why it is? X equal to 1 taken example. Therefore, X equal to 1 means same turns on both sides. So for the same turns in this transformer, we are getting same voltages on both sides. So we call it is 1:1 transformer. Okay, or isolation transformer. We are just comparing by X equal to 1, but generally we don't use X equal to 1. Very rare cases we use that for isolation purpose only. Otherwise, mostly either step up or step down applications only we go. Okay. For this X equal to 1, all connections, when you compare, you will get some relations. Which connection will give high voltages, which connection will give low voltages. So these are all objective type of questions. Okay. Now let's see the vector group, which vector group it is. Completed all of this one. When offline classes will start? So that we should, everyone knows that is mostly by this year we cannot expect, almost by next year only. Thank you, Akash. By next year only we can expect offline classes. Okay, good. See, offline classes will be still better than this. Online is I don't like online first, but due to the situations we need to proceed like this only. But offline is always best. We can start. There is no lockdown. We can start, but problem is what? Hmm, Problem is up to the cases almost reduced. It is not preferred to start because most of the people may not come. Some of you comfortable in online also, but in online only one thing is from starting also I'm saying in online classes the complete care should be taken by the student on, because we are not having any command, just we are here and we are not seeing anybody, and you only need to concentrate well, and you only should attend properly in time, and you should follow properly. Okay, that is completely your responsibility. Yes, outcome terminals means outcomes. Primary side, what are the outcome? Secondary side, what are the outcome terminals? Okay, next, let's see the vector group. How to say vector group? Primary side, you draw directly. Which connection is there? Primary star is there. So draw star connection. So before drawing, you need to check one time. In star, which three are joined as neutral? A1, B1, C1 are joined. So A1 should be at neutral. This is A1. This is A2. A phase it is. Okay. You can draw this A like this also. Anywhere you can draw. Anywhere you can draw three phases like this. But why I taken A towards like this vertically up? Because I need every time A I'm comparing in all clocks. That's why A I taken pointing towards 12. Okay. So this is A phase. Next, B1, B2. Start from A1 only. A1, B1, C1 join. So from here B1, exactly 120 degrees we have to take, because three phases, 120-degree displacement. This is B1, this is B2. B phase it is. And from the same point C1 it is. Again 120-degree displacement. 120 degrees. This is C1, C2. C phase it is. Clear? So ABC. Like a star you have to draw. Previously we have drawn in order to get like a delta, but now star. So primary star is drawn. This is over. Next, secondary star. Secondary side only important always. Primary directly you can draw this delta or star, anything. Now observe before drawing secondary one time. Which three terminals are shorted on secondary? A1, B1, C1 only shorted. So from the neutral, this is A1. Now draw A1, this is A1. Now A2 you should draw. How? Where you will draw A2? Drawing secondary always exactly in phase with primary. So draw parallel. This is A phase. A1 here, A2 here. Now A both coincide. A1, A2 terminals coincide. A2, A2 also coincide. A1, A1, A2, A2. Similarly, B1, B2, B phase, C1, C2, C phase. Okay. Yes, primary star, secondary star. We got. Now, can you directly we compare in a clock or not? Yes, directly you can compare. No need to draw delta here. No need to draw delta because directly a star connection you take in a clock connection. Okay. See, primary phase A. This is primary phase A, and this is secondary phase A. This is on neutral of secondary, neutral of primary. Let us coincide both. Let us coincide both the stars, one over other. Then exactly at the neutral coincides, then small a, capital A will come exactly in phase. So this is capital A, this is capital A, and very small a, exactly in phase it is also coming. Small a also coming exactly in phase. Then what is the angle between these two? 0. So this is 0-degree connection. Or with respect to clock, what is the clock it is? How much time? 12 o'clock. So this is 12 o'clock connection. 12 o'clock connection. Or how we represent in short, it is capital Y, primary star, secondary small letter, small y. Or N also you can take. Whether you are taking N or not, that is not a matter. That is your wish. YY, 12 o'clock connection. YY 12. Simply we represent YY 12. YY 12 it is. Okay. YY 12. Very good, Jadov. You completed all star delta star and star delta also, right? Good. YY0 also. You can take it as YY0 also. YY12 or YY0 both are same. But generally we take YY12 because in a clock we never indicate like 12 0 o'clock. So we call like 12 o'clock. No, that's why YY12 or YY0 also you can take. Now similarly draw second connection in star star. Second 180 degrees. This is 0-degree connection. To draw the 180-degree connection. So for second connection, what you will do is don't change primary star. No need to change primary. Secondary side, let us short now A2, B2, C2 as neutral and open here. Load is connected at A1, B1, C1. Then check which connection you will get. 180 degrees you will get. Okay. Next, second connection. Second. Primary side, I'm not changing. And one more observation is, so all of you, whatever I am drawing figure, try to draw 100% same diagram. So I will draw now how most of the people will draw generally in the classes. So don't change the diagram 100%. 100%. The little line also should not change. Draw like that. Because if you don't draw like this, I will tell you how the people will draw. Just wait. Just wait 1 minute. A1, B1, C1. B2, C2. Now primary side I'm not changing. It remains same. Neutral is this. But secondary side, now I will short these three, A2, B2, C2. Any three you can take as a neutral, anything, same value, same voltages, nothing will change. Only vector group will change with this. Now, source is same, A2, B2, C2, and load is A1, B1, C1. Same voltages, no voltage magnitudes will change, same only. Only angle, vector group will change. Now, what what is the observation? For star, no problem. Now, I will show you in delta previously. Observe this connection. How the people will draw here is, in while drawing delta, like this, most of the people may draw. Check yourself. A phase, B phase, C phase. A1, B1, C1. A2, B2, C2. Now observe, while drawing delta particularly, so I am joining, for example, A1, B2, no? A1, B2. So I joined like this. But some of you may also drawn like this. Check your diagrams. Maybe some of you has drawn like this. Okay. Some of you may be drawing like this. Don't draw like this. Why? Because see here some part of wire you are leaving. What it means, after some time you will get doubt. This is also like outcome coming outside. This is also coming outside. Now here A2 is coming outside. This is also looking A1 is coming outside. So which terminal is coming outside? A2, B2, C2 actually we are taking outside. That why terminals we take outside. There we give supply. But don't draw like this. Okay. Draw exactly from the end of this terminal. So that clearly we will know these are our outcomes. Okay. Yes. Okay. Now primary star we are not changing, same. Secondary star, how we changed? A1, B1, C1, we are connecting load. Anywhere you can connect. Now this is our 180-degree connection. So if you draw vector also, you will get same as it is. Primary star same, A1, A2, B1, B2, B1, B2, B phase, and C1, C2, C phase. Okay, primary star no change. Now secondary, which are sorted here, A2, B2, C2 sorted. So at the neutral A2, this is A2. Now where is A1? You should draw downward or upward. For that you need to observe your primary FS. So if it is A2, check primary side. A2 is at the top, A1 is at the bottom. So if it is A2, A1 should be here. Okay, AFS, both parallel in phase. Similarly, this is B2 because A2, B2, C2 shorted. That's why I'm taking everything from neutral. This is B2. Now where is B1? It should be in this direction. If it is B2, B1 is here. This is B phase. Check B phase, both in phase and satisfied. Similarly, C2, C1, C phase. So this is our secondary star. Now take a clock and place it is any phase you can take, A phase, B phase, C phase. Angle you will get. But for a proper clock, we need to point the minute hand always or long hand always 12. That's why I'm taking capital A is reference always at 12. Then if you draw this, capital A pointing 12, pointing 12. Now let us place this neutral and this neutral coincide each other. Then small a you will get exactly opposite. So small a is coming exactly opposite. Small a. This is hour hand. This is minute hand. And this is how much? 180 degrees. 180-degree connection or 6 o'clock connection or simply YY6 connection it is. YY6. Start 6 o'clock. Got it all of you now how to draw this? These two are easy. These two are easy only. But delta star and little most confusion is star delta. That star delta itself I am leaving to you first. Let's see how many of you will draw. So already one of the One of you drawn completely. How we drawn in B 180-degree connection? Which B? This small b, no? So this is B2. Now you should draw B1. So where you will draw this, how you will draw B phase? Small b you should draw parallel to primary B phase. So parallel means this one, or like this also parallel. But if it is B2, where is B1? Check here. B2 is here, B1 is towards the upward side. So from B2, B1 is towards this, not downward direction. Okay. So anyhow, that is one way. Other way, what I said, when you are drawing, you should get clockwise ABC. See, if it is A, B you should get here only, not here. Okay. Yes, good. Clockwise only. So these are the two connections in star star we have. Now let's see the features of star star. Features. So completed all of this. Okay, right. Right now, features of star star. Features of star star. Now, however, we have seen for delta delta, same as it is in star star. Same points again will repeat, but opposite to delta delta. In star star, what is the phase voltage? Line voltage by root 3 times. Means phase voltage is less or not? Yes. Phase voltage is less, but line voltage like delta delta same 11 kV, but phase voltage is less in this. So whenever phase voltage is less, how many turns required per phase? Less number of turns. So write that point. As V phase equal to VL by root 3, this connection requires less number of turns per phase. Less number of turns per phase compared to delta delta. Compared to delta delta. Okay. For same voltage rating, we are comparing delta delta and star star. Then star will require less compared to delta. Next, second point. Same as V phase equal to VL by root 3. What is the insulation required as it is low voltage per phase? Low voltage per phase. Insulation required also reduces. Right, that comma it requires less amount of insulation. Less amount of insulation compared to delta delta, it is also less amount of insulation. Next point. Next. Next, as what is the phase current in star star? Phase current, line current, both are same here. I phase equal to IF. Phase current, line current, both are same. Line current is actually high, which is equal to phase. So phase current is the high current here. As current rating is high per phase, you need thick wire compared to delta delta to withstand that high current. Right, comma, it requires a wire, a thick wire compared to delta delta. Okay, next, 4. What is the voltage relation? Same as it is delta delta or not? Yes. If you give voltage V1, same voltage you will get V1 when there are same number of turns per phase. Write that point also. For an input voltage, of V1, this connection produces produces an output voltage of V1 when same voltage for same number of turns, comma, for same number of turns on both primary and secondary. Okay. Now, what is the nature of EMF induced? For star, EMF induced in the winding is dash sinusoidal or peaky wave. Answer is both. Why both? We have two types of magnetic circuit again, core type and shell type. Suppose star winding we are using in core type transformer, 3-limb core type. What is the shape of EMF? Sinusoidal. If we use the same star for shell type, what is the shape of EMF induced? Peaky wave. So in the yesterday's class, we have seen types of magnetic circuits. There I given the statements why it is peaky, why it is sinusoidal in core type transformer. Okay, so write that point individual. Next, fifth point. The shape of EMF induced. The shape of EMF induced in this connection is sinusoidal for 3-limb core type transformer and it is peaky wave, non-sinusoidal peaky wave for which type of circuit? For 5-limb shell type transformer. For 5-limb shell type transformer. So at this point we know already, same point we are writing again, because two cases possible. For star core type different, shell type EMF is different. Next, sixth. Now this star suitable for both type of loads or not? Star, primary star, secondary star. So as it is star connected, you can connect a 3-phase load, or due to availability of neutral, you can also connect a single phase load. Both are possible in this, but delta only 3-phase, because neutral is not available there. So right here, due to availability of neutral, it is suitable for single phase loads as well as 3-phase loads. Okay, suitable for single phase loads as well as 3-phase loads. Now there is a problem of this connection only with 5-limb shell type. There is a problem of this star only with 5-limb shell type transformer. What is the shape of EMF there? Peaky wave. Now can you give this peaky wave to transform load? No. The EMF is peaky means the load insulations may damage due to the peakiness in the voltage. Peak value is very high, suddenly peak. Actual sinusoidal less peak, but in the peaky wave, magnitude of peak is increased. Due to that highest peak value, insulations will damage. Now we need to provide, or we need to make EMF sinusoidal in shell type also. Now let's see how to make EMF sinusoidal for shell type transformer also using star. Write that. First write drawbacks, then we see. Right, drawbacks. Starting drawbacks of star transformer with the 5-limb shell type core. 5-limb shell type core. So what is the problem of or drawback of that star-star transformer when we use in shell type transformer? First, the EMF induced is the EMF induced is non-sinusoidal. Non-sinusoidal, what is the shape that is? We call peaky wave. Non-sinusoidal, that is peaky wave. So peaky wave means what is the total EMF? You have the EMF totally having odd harmonics, peaky wave, odd. So in that we are taking mainly fundamental third harmonic, and higher order we are neglecting. Only fundamental third harmonic we are considering now in everywhere. Now therefore, let's see what is the problem exactly due to this third harmonic EMF. See, this E1 fundamental we call fundamental. E1 is fundamental. This is third harmonic EMF. Now this is in equation we are writing E1 means what? EM1 sine omega t. Like that, E3 means what? EM3. Equation representation it is sinusoidal signals representing like this EM3 sine 3 omega t, like that, and so on, all harmonics. This is representation using signal or equations. Signals representing using equation. Now same signals we will represent in vector form. Phasors, how fundamentals we draw like this. Three phases now, A phase, B phase, C phase. Let in A phase fundamental is here. And where is B phase? 120 degrees. This is EB1, fundamental in B phase. Each phase having fundamental EMF, third harmonic EMF. So this is in C phase, fundamental, EC1. Okay. So whenever there is no third harmonic, if there is only fundamental, what is the shape of the EMF? We call sinusoidal. Now, when there is only fundamental, these phasors are rotating in space. Vectors, conventional direction is what? Anti-clockwise. We consider anti-clockwise always. So these vectors are rotating. At what speed the vectors are rotating? This is omega, sine omega t. So this is the speed, radians per second, omega. So with that speed, the fundamentals are rotating in anti-clockwise. They are rotating in space, but we consider at one instant here. Okay. This is our neutral. The neutral is here stable. If there is no third harmonics, the neutral is called stable neutral. Neutral is fixed. Then only vectors will rotate here continuously. Okay. Now observe what happened due to third harmonics. Now there is a third harmonic EMF also in this shell type core because of star-star transformer. When there is third harmonics, so in addition to this fundamental, third harmonics also there in space here. EA3, EB3, EC3. Why all in phase? 0-degree displacement or zero sequence we call. EA3, EB3, EC3. All are in phase here. That is we call co-phasal nature. Now this third harmonics also rotating or not? Yes, they are also rotating. Now first of all, when there is a third harmonic, because of the third harmonics, this neutral will shift from this location. Suppose there is no third harmonic, neutral is what? Stable, fixed at one point. But due to this third harmonics, the neutral will not be here. The neutral will come to some other position. Let us take here. It will shift from the original location. Now neutral is here. Now neutral not only shifted, it will also rotate. Neutral also rotate in the space. In the same anti-clockwise direction it rotates. At what speed it will rotate? That depends on, observe. Fundamental vector speed is omega. Third harmonic vector speed is 3 omega because 3 omega t it is. Okay, 3 omega t. So third harmonics also rotating in space with a speed of 3 times of fundamental, very high speed when fundamental is rotating at omega. Now, what is the speed of this neutral? Neutral also rotating in the space. Neutral also moving here, oscillating we call it is. Neutral also moving in the same direction. But what is the speed or velocity of this neutral? How much? Just the relative speed between these two vectors. This is 3 omega. This is omega. So if two bodies moving in same direction with the different speeds, What is the relative speed between the two? Difference. Take the difference of these two. Then what is the difference? 2 omega. So this neutral is rotating with a velocity of 2 omega radians per second. This neutral, see at one instant neutral here, at one instant this is neutral. After some time here is the neutral, here is the neutral, here is the neutral. So like that neutral rotating. This neutral we called oscillating neutral. Oscillating neutral. Now I will tell you exactly what is the problem. Yesterday, if you remembered, so there I said for a star connection transformer, what is the shape of phase EMF? Peak wave. But what is the shape of line voltage? Fundamental or sinusoidal. So there I said you can connect three-phase load, because three-phase load means what is the line voltage is only fundamental, sinusoidal, no problem. But can you connect single phase load there? No. Why single phase load you cannot connect? Because third harmonic also there in that per phase. So actually what happened due to this third harmonic is, as neutral is oscillating, the phase, single phase loads will not get same voltage continuously. Load voltage also oscillates. Suppose you are single phase load now in your home. Suppose if neutral is oscillating like this, in your home, if you switch on the light, your light also oscillates. Oscillates means bright, dark, bright, dark, bright, dark continuously. Then is it preferable? Or if you give supply to motor, single phase motor speed increase, decrease, increase, decrease, fluctuations will be there. Then this type of fluctuation should not be allowed for loads. Load will damage now with this. Load will damage. So due to oscillating neutral, see, whenever neutral is here, this is the phase voltages. So I will show you clearly with some other diagrams, just right up to this. Just right up to this. Take the figure. Neutral is moving. Why? Because of third harmonics. Because of third harmonic, neutral will go away from this point. Now not only going and also rotating. Why? Because of this relative speed, approximate 2 omega radians per second. All these questions are previous some of the examination questions. So in star transformer with shell type core, the neutral is dash, fixed neutral, oscillating neutral, or anything like that options. Or the neutral is oscillating at what speed? Omega radians per second, 2 omega, 3 omega, 4 omega. Answer is 2 omega radians per second. In what direction neutral is oscillating? Clockwise, anti-clockwise, or in both directions? Answer is anti-clockwise, because vector direction anti-clockwise. Neutral also oscillating in same direction. Now what is the problem with oscillating neutral? Whenever neutral oscillates, the phase voltage will not remain constant. Phase voltage also oscillates. Phase voltage means one phase to neutral. Neutral is moving. See, whenever suppose A is point A is here. Whenever this neutral is oscillating, when at one time neutral will come near to A and going away, more away. So whenever it is moving like this, magnitude of voltage also fluctuated. So this type of voltages we don't want for loads. We need a constant voltage. Okay, this is called oscillating neutral. Right. Second point. Right here, second point. See, this is relative speed concept. See, two bodies moving in same direction. One is at 60 kilometer per hour and other is at 40 kilometer per hour. Then what is the relative speed between these two bodies? Additive or subtractive? Difference of these two, no, that is 20 kilometer per hour. Then this is not 100 kilometer per hour. Suppose you are sitting in one bus, your friend is sitting in one bus. So both are moving side by side. Both buses are moving side by side at almost same speed. Then what is the difference? Both look stationary or not? Yes, zero. Or if it is different speed, then slight low speed you can observe there. So same this is. Then how it is 4 omega? Clear? Right, second point in this. Due to third harmonic EMF, due to third harmonic EMF, the neutral of fundamental, the neutral of fundamental, the neutral of fundamental is shifted and also rotating, and also rotating in anti-clockwise direction, in anti-clockwise direction with a velocity of, with a velocity of 2 omega radians per second, 2 omega radians per second. It is called as, comma, it is called as oscillating neutral, oscillating neutral. Okay, next, third point. So as neutral is oscillating, single phase voltages oscillates. Voltage magnitude variations will be there. Due to that single phase load, we cannot connect. If you connect, loads will damage. Write that point. Due to oscillating neutral, due to oscillating neutral, the single phase voltages also oscillates, hence it is not, it is not preferred, it is not preferred to connect single phase loads, to connect single phase loads. Okay, it is not preferred to connect single phase load. Single phase load, when you connect, voltages is fluctuating, your load also damaged or fluctuated, whatever the load you connect. Now let's see how neutral is oscillating. So I will give you some different instance positions of fundamental and third harmonic. Then you will understand how neutral is rotating. Okay, right, make a note of this. Note, see, total EMF induced in winding is what? Peak EMF in each phase, E1 plus E3, fundamental EMF plus third harmonic EMF. Now I'm considering initially, let at omega t equal to 0. At some instant I will take, at one instant, fundamental and third harmonic. See, at omega t equal to 0 here, let this is my EA1 fundamental EMF, EA1, EB1, fundamentals always 120-degree displacement, EC1. Okay, EA1, EB1, EC1 plus third harmonic EMF. Where is third harmonic EMF? All in phase only, no? So all are in phase. So I'm considering initially this is EA3, EB3 also in phase, but I'm drawing side by. This is EB3 and this is EC3. Okay, all are in phase, but separately I drawn to shown like this. So all in phase, EA3, EB3, EC3, and fundamental ABC is here. This is at one instant, at one instant. Now, if there is no third harmonic, no, suppose no third harmonic, the neutral is here only fixed. Neutral is here, but due to this third harmonic EMF, now along which direction third harmonic EMF we considered? In the upward direction. So this neutral will shift in the same direction now to some magnitude. Suppose Magnitude of third harmonic is how much? Small, no? Suppose this much magnitude, no? This length is suppose 1 centimeter, for example. Same 1 centimeter length, whatever magnitude of third harmonic is there, this neutral, actually, this is the neutral point for fundamental. Okay. Now I will add this third harmonic to this. Then what happened? Actual neutral is here, this dotted line, but neutral little shifted here. Neutral shifted. Then this is EA1, EB1, EC1, EB1, EC1. So these magnitudes are different or not? Yes. EB1, EC1 little increases, EA1 little decreases. Magnitude of this EA1 little decrease. Okay. This is the neutral point now at one instant. Now let us take some other instant. So they are rotating. It is rotating at omega. It is rotating at 3 omega speed. Now I will take one more position. Suppose at angle omega t equal to, for example, 90 degrees or 30 degrees. I will take first 30 degrees. After 30 degrees, it means after 30 degrees, fundamentals rotated by 30 degrees. Fundamentals rotated by 30 degrees. Check now. This is neutral. This is my reference dotted line, 0 degree it is. Now EA1 will rotate by 30 degrees. This is EA1. (30 degrees) rotated. Okay. After 30 degrees I taken. Now remaining two also will rotate by same 30 degrees. So EB1 here. Now it will be here. EB1. Now EC1. EC1. After 30 degrees it is. Now what happens to third harmonic? Tell me now. How much angle third harmonics will rotate? How much angle third harmonics will rotate? 90 degrees they rotate. Why? What is the speed of that? 3 omega, no? If fundamental rotated by 10 rpm, they will rotate 30 rpm because 3 times of that. So due to that, if it is 30 degrees shifted, it will shift by, or it will rotate by 90 degrees, like this, like this. This is EA3, EB3, EC3. Now how the resultant of these two? How the resultant? Actual neutral position should be here, but now along this third harmonic direction, neutral will shift. Okay. Now this is EA1, this is EC1, this is EB1. Now clear all of you how neutral is moving? Like that, neutral oscillating. Now previously neutral is here, neutral is here. Now same neutral arrived here. Like that, neutral is rotating. In whatever the direction third harmonics are rotating, neutral also rotating, like this. Now magnitude is changing or not? Yes. Now observe, what is the magnitude of EA1, EC1? Less. Which magnitude is looks like more? EB1 magnitude is more. Like that, every phase voltage continuously vary here. Every phase voltage continuously vary. Now clear how the neutral is oscillating and how the magnitude of phase voltages are changing, like this. And if you take 90 degree, omega t equal to 90 degrees, I'm not drawing, you draw this. At omega t 90 degree means fundamentals rotated by 90. Then how much angle third harmonics will rotate? 3 times. 90 into 3 means 270. So this is our 0 degree reference. This is 90, 180, 270 means here. If fundamental rotated by 90 degrees, third harmonics will rotate by 3 times, 270 degrees. Then you can draw again resultant. So like that, neutral is oscillating. Clear? When neutral is fixed, suppose there is no third harmonics, 0. Is the neutral will move now? No. Neutral will not move. But this third harmonics will make the neutral to shift. It will affect that neutral point in the fundamental. Okay? Clear all of you this one? Yes. Now clear all of you this. Neutral oscillating, magnitude of each phase is changing. Yes, Srikanth, right. Still, we are not coming up to that. So we will come. Wait. In 90 degrees, you check. Draw the figure. Yes, EA1 magnitude will increase in 90 degrees, right? In 90 degrees, EA1 magnitude will increase, right? Okay. So this is just I have shown. So no need to give this information. Just given how neutral is shifting. Maybe you are getting doubt. Because of this third harmonic components will make the neutral to shift. If there is no third harmonic, neutral will not shift. When there is only fundamental, shape of EMF is what? Sinusoidal. Then neutral will not shift. Only phasors are rotating in space. Clear? In 0 degree, there is effect of EB3 on EB1. Because of that total neutral shifted, now all phase voltages changes, no? Okay, next. Now let's see how to make this EMF sinusoidal in shell type transformer also. Okay, you know already previously in the yesterday class I given when there is a star connection, how to make EMF sinusoidal by providing neutral grounding. So that method we will see here. Right side heading. Methods to produce side heading. Methods to produce sinusoidal EMF. Sinusoidal EMF in star-star transformer. Sinusoidal EMF in star-star transformer with shell type magnetic circuit. With shell type core, simple. With shell type core. Only in shell type core we have the problem. So that is we will reduce by using some methods. Let's see what are the methods to make sinusoidal EMF in star-star transformer for shell type. So already you know one method. What is that method? By providing neutral grounding along with source neutral also. If you provide neutral grounding, then third harmonic current will circulate, EMF will become sinusoidal. Same thing we will hear. One method is that, and there is other method. You will see that. Write the first one. Write the first point. By providing, this is already we know. By providing neutral grounding, neutral grounding of primary and secondary, primary and secondary windings, primary and secondary windings along with source and load, along with source and load. So we should provide neutral grounding for source also. If you provide only winding, no use. Okay, so take the figure for this. Take the figure. This is primary winding, star connected. And secondary winding also, star connected. Primary star, secondary star, and source we are giving no source. Let this is the source, primary side, three phase alternator. Similarly, secondary side, what we connect, load will connect, three phase load. Let us consider this is our three phase load, some star connected three phase load, for example. Okay, primary winding, secondary winding, primary side source connected, secondary side load is connected. Now, what is exact statement? You should provide neutral grounding. Neutral grounding. If you provide only winding neutral grounding, is it enough? No. Source also should be grounded. And if load also there, neutral grounding. Okay, this one. So if you provide both neutral grounding, previously we have seen, now there is a path for third harmonic current through this grounding effect. Now third harmonic current will circulate. Already there is fundamental plus third harmonic also will flow now. Now, what is the resultant current flowing in the winding? Peaky wave. If current is peaky, flux is sinusoidal, EMF also finally sinusoidal. So we know already this. But this is not the best method. In order to make EMF sinusoidal, this is not the best method. Means purely sinusoidal, you may not get in this method. Even if you provide neutral grounding, you don't get purely sinusoidal EMF in these windings. Why it is? There is a drawback of neutral grounding still, because I3, this I3 taking its closed path through what? Tell me, through what it is flowing? Through grounding and through this transmission lines. See, is source is nearby? No. Source transmission line. This is transmission line, sending and receiving and transformer here we have, and this is supplying to the load. Now this is a long transmission line, for example, and this is having, this is what earth it is, neutral grounding. Because of grounding, there is some impedance of that grounding. Let Z grounding impedance, and this is transmission line. This transmission line having some impedance. Let ZL, and our transformer windings will have some impedance. Let Z1. Now, what is the total I3? I3 is due to third harmonic EMF. Yesterday we have seen due to E3, I3 is flowing. Now, what is the total current? E3 by Z1 plus ground impedance plus transmission line impedance. Then what is this overall impedance? Very high it is. It is not small impedance. It is high impedance. Then what is the magnitude of current? Very, very small. Now I will still give clear idea how EMF will not be completely sinusoidal. Observe. Initially current is sinusoidal, fundamental. If current is sine, what is the flux produced? Flat top, phi 1 plus phi 3. Okay. This is our flat top flux. Now due to that flux, EMF induced, fundamental EMF, due to phi 3, E3 will induce. Now due to this E3, I3 is flowing, third harmonic current. But what is the magnitude of current flowing? Very small. Why? Impedance offered to the current is very high, no? So current is very small. So due to the small third harmonic current, how much magnitude of third harmonic flux will produce? A small third harmonic flux will produce. So is this third harmonic flux will compensate completely the actual third harmonic flux? No. This is higher magnitude. Suppose 100 flux lines it is, but the produced third harmonic flux lines is just 60. Now 60 will compensate, but still there is some small amount of third harmonic flux. Due to that, there is still small amount of third harmonic EMF completely not eliminated. Then what is the shape of EMF induced in the winding? Is it purely sinusoidal? No. Still it is having some peaky nature. Due to this, this is not the best method to use. What is the best method? There is one second method. If you want to make completely sinusoidal, the second method is by using tertiary winding. The second method is tertiary winding. So first take the figures and below that write 1 point. First take the figures. Neutral and ground and all these terminology you will get in your protection. So you concentrate there itself. We are not discussing here. Neutral is the combination of three phases. Neutral point. That's it. That should be provided to ground for protection purpose or anything. You have different grounding methods now again. Neutral grounding, solid grounding, or reactance grounding, or resistance grounding. So there you learn completely. So right below this one point, like in this method, load side is not compulsory, but if you ground, still better for protection purpose and all. Right. In this method, the EMF induced in the winding will not become purely sinusoidal. In this method, the EMF induced in the windings will not become purely sinusoidal since the magnitude of third harmonic current is less since the magnitude of third harmonic current is less due to the high impedance offered by ground the high impedance offered by ground and the transmission line due to the high impedance offered by ground and the transmission line. Next, second point. Second method. One method is grounding. Second method is right by using tertiary winding. By using tertiary winding. By using tertiary winding. So we will place one more winding on this transformer core. One more winding we place. So due to the tertiary winding, as you place one more winding, this tertiary winding is a delta connected winding. That is important. You should use one more winding and that winding should be delta connected winding. Then only it will work. Otherwise, no use again. If you take one more star connection, that must be delta connected. See the figure for primary star. Primary star, secondary star. Now, in the same transformer, we will place one more winding on the core. That winding is a delta connected winding, also called closed winding. It is closed. Take a winding just having some number of turns, like a closed winding. You can call delta connected winding or closed winding. It is one more winding is placed. That is a tertiary winding, which must be delta connected winding, also called closed winding. Closed winding. Then only it is suitable. Otherwise, no use of that star connection. If we take one more, how here it will make EMF sinusoidal is observed. When you give sinusoidal supply, current is what? Magnetizing current, sinusoidal. Then what is the flux produced? Flat top, phi 1 plus phi 3. Then it is causing E1 plus E3. E1 plus E3 in all the windings. Not only in this, here also you will get E1 plus E3 because same flux will touch all the windings. No, here also you will get E1 plus E3. Suppose initially you will get, but observe due to E3 in this tertiary winding, immediately a path will come for third harmonic current. Sum of fundamentals is what? 0 in this delta. But sum of E3 will not be 0. No? Already we know from yesterday's concept that is. Now immediately I3 will circulate. Now this I3 will produce a flux phi 3. Now what is the magnitude of I3 here compared to previous method? In the previous method, I3 is flowing but small magnitude due to high impedance. But now as we are using a copper winding, a copper winding. What is the impedance of that copper? Very, very less compared to grounding or transmission line and all. So now magnitude of current is high. The phi 3 produced is also high magnitude. Then this phi 3 and the main phi 3 gets cancelled according to Lenz's law. Both opposition get cancelled each other in the core. Once they cancelled, what is EMF induced in the windings under steady state? Only sinusoidal. The EMF in the windings will become sinusoidal once you place this tertiary winding, which is delta connected winding. Now, once E3 becomes 0, now this E3 will become 0 in this. There is no third harmonic in the EMF in the windings. Then only fundamental. Now, when there is only fundamental, what is the neutral of that star connection? EA1, EV1, EC1. Once E3 is 0, the neutral of that star connection will be stable or not? Previously neutral here. Now it will go to back again fixed point. Previously neutral is here. Once E3 becomes 0, as there is no third harmonic voltages, now the neutral will go to its original position again and becomes stable. Therefore, as neutral is becomes stable by placing tertiary winding, this winding we also called as stabilizing winding. This winding we also called as stabilizing winding. Why stabilizing winding? Because of this winding only neutral becomes stable. That's why we call it is a stabilizing winding. Okay, clear all of you this point? Now, in interviews, many times one question they asked on this tertiary winding concept. That is there any other use of the tertiary winding here? Is there any use of tertiary winding? One main purpose is what? To make the EMF in the winding sinusoidal, we are using this tertiary winding. That's it. Can we use this tertiary winding for any other purpose? Any other purpose means to supply any other load? Yes. If you take, here we are not taking any terminals outside. Observe, any terminals we are not taking outside. Now let us take the terminals of this tertiary winding also outside. Take outside from the transformer. Now you can connect some loads to this tertiary winding also, because fundamental EMF is there or not? Yes, it is there. Now you can use that voltage for any other loads, mostly in some substations for auxiliary equipment. Like in substation we have some other equipments now for protection purpose and all, and for that purpose we can use the tertiary winding to supply the load. Like that we can utilize this tertiary winding for auxiliary power supply in the substations. We can use that. When we can use? If you take the terminals outside from the transformer. Otherwise, if you don't take, the only purpose is to make the EMF sinusoidal. Clear all of you this second point? Yes, protection purpose. Okay, so with this we stop here. Star star is completed, and tomorrow we see delta star and star delta. So when you place the tertiary winding, which is delta connected winding, on the same core, what is the EMF induced in this star star transformer? Peak E wave. Now, when you place this tertiary winding, no, in this also peak E wave will come. That is E1 plus E3 will be there. Now, due to this E3, what happened? There is a path for current or not? Yes, there is a path for third harmonic current in this I3. Now that I3 will flow, and due to that I3, a flux phi 3 will produce, and this phi 3 will cancel the actual phi 3 produced. Then both cancel means the resultant flux will be sinusoidal. EMF induced in windings also sinusoidal. Okay. On the same core you place, because suppose on the limb you place star sternum, there is yoke, that is horizontal part, so there you can place the tertiary winding anywhere. Tertiary winding is suitable for auxiliary power supply. We can use it for auxiliary power supply. Yes, tertiary winding only one. Yes, in the first method you can connect three phase load. Three phase load, no problem at all. Problem for single phase loads. that fault conditions you see in the protection system. Tertiary winding is only one. Okay. Yes, 3-winding transformer. It is a 3-winding transformer.
Hello, sir.
Tell me.
Sir, in 13F, sir.
Hmm.
Sir, I didn't get that neutral shifting. How can you explain?
Hello.
Because of third harmonic, neutral is shifted, no? Because that is I given with these figures here.
Hello.
Wait.
Sir, am I audible?
Wait, Arjun. Wait.
Okay, sir.
Tell Tulsi.
Sir, how is the point shifting? I didn't get that, sir.
So this is the reason, these figures. So if you combine these two, this neutral will shift along the direction of third harmonic EMF.
Okay, it's upwards.
In the direction of that neutral is shift.
Okay. So here, left side it is moving the neutral.
Yes.
Okay, sir. Okay, sir. Thank you.
Okay. Arjun, tell me.
Sir, I was also having a same confusion over that.
Okay.
So since the in the A phase, both the third harmonic and first harmonic are on the in phase, so they must be added together to get a higher output. And similarly in the B and C, the vector sum would be lower, so in effect the neutral should be shifting downwards, right, sir?
Yes. Your doubt is what? Neutral is shifting in what direction?
Downwards. So in effect, it should be from that figure, it should be shifting downwards, and on also in the second case for the omega t is 30 degree, it should be shifting rightwards.
Leftward, because E3, EA3, EB3, EC3 pointing in this direction, no? Left side.
Okay.
So
Yeah,
whatever.
but the
हिंदी में पूछना, हिंदी में नहीं, हिंदी में पूछ.
Sorry, I am from Kerala, that's why.
Okay.
Actually, sir, let's take the first case.
Okay.
In that case, the A phase, the first and third harmonics are in phase, so that they must be added.
Yes, good, right.
And in the C phase and B phase,
in the second case.
No, in the first case itself.
Okay.
And the B phase and C phase, the vectors are just opposite, not correctly 180 shift, but the vector sum would be lesser compared to the original phase voltage, right, sir? So in effect, the neutral should be shifting downwards, right?
Okay, you are considering magnitude of EA1 will increase, okay?
Yeah.
Okay, but according to your phasor exact in phase calculation, that is okay. But I have shown that how neutral is shifted, just that like that approximately, because people will understand easily here as these pointers are pointing in this direction, neutral is shifted along that direction I shown. I'm not considering any magnitude, just according to figures, you are considering this is less, this is more, like that. Okay.
Okay, sir.
This is not important. Anyhow, neutral is shifted, no?
Yeah.
Yes.
Yeah.
Okay.
By that way also, I was getting the clockwise rotation of the.
Yes. Okay.
I just had this confusion. Thank you, sir.
Okay. Good.
Good evening, sir.
Yeah. Got it.
In in induction motors, we have like a star delta status now, sir.
Induction motor, star delta status.
Sir. Like what we did in lab was after the starter starts functioning, we'll get some sound. After that only we need to proceed for the further instruction. So what's the reason for sound, sir? There like star delta
Anytime have you started with star delta motor first?
No, sir.
Then you are just observing, or maybe somebody has told you.
Okay.
Not sound. So when you in star delta means what first? That
Star.
is limiting starting current. So
Yeah.
first we will use that handle to towards the star side,
Okay.
star connected winding. There with star connected winding, current drawn will be reduced.
Yeah, okay.
Okay, low current will flow, so no problem to motor. Now motor will try to start.
Okay.
So whenever it is starting, so it will make little more noise, because little starting high currents will be there little. Due to that, it will little try to start rotating. After rotating for some time, then only you should move that handle to delta side.
Okay.
Not immediately again,
Okay. Okay.
because motor should rotate for some time, so that speed little increases. Whenever speed increase, then slip decreases. So you will understand there in that concept particularly.
Sir, if
So
you
after
suddenly
reaching for
do,
some time only, we should move to delta, not immediately.
okay, if you suddenly do, more circulating currents will get. Correct.
If you suddenly move, no, without motor is rotating, still
Yeah.
high current will flow, motor
Mm.
will damage.
Damage. Okay, sir.
We should
Yes.
not immediately.
Yes, sir. Sir, in 17F, sir.
Mm.
Sir, in this like secondary side, star connected is there, no, sir? In that initially E1 plus E3 will be there, sir, or initially empty? Initially, will we have any voltage, sir? Like zero. Initially zero ఉంటుందా లేకుంటే E1 plus E3 కూడా ఉంటుందా అని అంటున్నా.
In what?
In right side at star connected is there, no, sir? Right side star.
Right side.
Yeah, that one, sir. Initially we'll have, sir, E1 plus E3.
Yes, initially just starting, but after once we started, in fraction of second only, ikkada third harmonic it will flow, and
Hmm.
immediately steady state EMF will be sinusoidal only.
Sir, initial గా ఎట్లా
So
ఉంటుంది,
here
sir?
even only will come.
ఇనిషియల్ గా కరెంట్ లేదు కదా, sir,
Initially అంటే
అక్కడ.
కరెంట్ ఫ్లో అయ్యేది ఇక్కడ కదా, కరెంట్ ఇక్కడ కదా ఫ్లో అవుతుంది ప్రైమరీ సైడ్.
అవును.
Then flux is produced due to primary current, no?
అక్కడ ప్రొడ్యూస్ అవుతుంది, సార్.
Same flux will flow in all the three windings.
ఓకే. ఓకే. ఓకే, సార్. సార్, ఇన్ ది
Okay.
సేమ్ స్లైడ్, సార్, ఇప్పుడు మీరు ఇక్కడ ఇంతకు ముందు కూడా లైక్ బాటమ్ లో ఇక్కడ డాట్స్ అని రిప్రజెంట్ చేస్తున్నారు కదా, సార్. ఇక్కడ ఒరిజినల్ ఇంకా విత్ హార్మోనిక్స్ అని, జస్ట్ రిప్రజెంటింగ్ దట్ విత్ హార్మోనిక్స్ అండ్ వితౌట్ హార్మోనిక్స్, సార్, ఫేజర్ డయాగ్రామ్ అనేది.
ఎక్కడ అది?
ఇక్కడ ఇప్పుడు కింద బాటమ్ లో ఫేజర్ డయాగ్రామ్ గీశారు కదా, సార్.
ఇదే
అక్కడ అంటే మీరు
yes, this is the neutral when there is harmonics.
విచ్ వన్, సార్, విత్ హార్మోనిక్స్?
థర్డ్ హార్మోనిక్స్ ఉన్నప్పుడు న్యూట్రల్ ఇక్కడ ఉంది కదా, నాట్ ఎట్ దిస్ పాయింట్. ఇది ఆసిలేట్ షిఫ్ట్ అయిపోయింది. బట్ వన్స్ యూ ప్లేస్ టెర్షియరీ వైండింగ్, ఈ న్యూట్రల్ అగైన్ కమ్ బ్యాక్ టు ఒరిజినల్ పొజిషన్.
ఇప్పుడు రెడ్ కలర్ కూడా ఒరిజినల్ పొజిషన్, సార్?
దిస్ ఈజ్ ఒరిజినల్ పొజిషన్.
ఓకే. ఆఫ్టర్ ప్లేసింగ్ టెర్షియరీ వైండింగ్.
ఎస్, ఎందుకంటే ఫండమెంటలే కదా, ఇంకా థర్డ్ హార్మోనిక్ లేదు కదా.
అవును. Okay, if tertiary winding is not placed, black one is the point.
Yes.
Okay. Okay, sir. Thank you.
Hello, sir.
Yes.
Sir, we will connect neutral to ground, no, sir. Then how can we assume that Earth is at zero potential?
That is reference, no, generally. Reference, that is
I
we
mean,
consider.
practically, how can we take that?
Practically means, is it generating any voltage? Earth is generating any voltage?
But it may have some minute voltages.
That is itself our reference. Something reference required for us to say some other potential. Otherwise, directly we cannot say this is the potential difference. No? Some reference we taken, Earth is like zero potential.
So practically also, would we connect like grounding? Do we use? Sir?
Definitely, earthing is must. In protection system, it will come clearly. Will listen there.
Is there any possibility that currents will flow from the ground?
Yes.
Then would it be a problem?
No,
For
not a problem. No problem, because okay, you listen power system protection. There you will understand clearly all these points. Okay.
Okay, sir. Thank you, sir.
So good evening, sir.
Tell me.
Sir, in the same page, sir, here the tertiary winding is magnetically coupled or electrically coupled, sir, in the transformer?
Both magnetically coupled.
Okay, sir. And you have said that is stabilizing winding, no sir? That is for tertiary winding, no sir?
Yes, yes.
Tertiary
Because
winding is
it is
stabilizing.
making the neutral stable, no?
Yes, sir.
That's
And
why.
okay, sir. There, the neutral, the I mean the constant neutral. Where are you pointing, sir? How you are pointing that, sir?
In the previous figures, neutral is here, no? Shifted. This is neutral, blue dots.
Yes, sir.
When there is third harmonics. But whenever third harmonics are zero, this neutral will come back to original position or not.
Okay, sir.
That means neutral is stable, to show that I given like this. Stable neutral.
Okay,
When there
sir.
is only fundamentals, neutral is the stable point. That's it.
Okay, sir. Sir, and one more, sir. In yesterday, you said something called open delta, no, sir. Can you tell what is that again, sir?
No, open delta will come in next after
Okay,
completion of 3 phase.
okay, sir. And that is magnetically coupled, no, sir?
Yes,
Okay,
I will show you that.
okay, sir. Thank you, sir.
Next, Abdul Rahman.
हेलो सर
Tell
सर
me.
मेरे को हेलो
Wait, Abdul. Both are Abdul only. Wait up. Abdul Rahman, tell me.
या
हेलो सर
सर मेरे को डाउट क्या है कि पहले
Bol. Tell me.
हेलो
Tell Abdul.
जी सर मेरे को पहले आप स्किन इफेक्ट के बारे में कुछ बता सकते हैं सर
Skin effect is
स्किन
what whenever alternating current passing through any solid conductor.
ओके
Actually, solid conductor. Suppose this is solid. Single
अच्छा
solid wire. Then whenever current is passing through this, current should flow in total surface area, no? Actually, but it won't flow. Alternating current will not flow. Alternating current mostly will flow on the surface or skin of the conductor only, not in complete cross section. Complete cross section means this is completely this is, but it won't flow in this complete, only on skin. That is called skin effect.
अगर वो डीसी सप्लाई दिए तो सर क्या होता
When you give DC, current will flow in throughout cross section. For DC, current will flow uniformly throughout the cross section. No skin
सर
effect.
वजह क्या है सर उसका इसका कुछ फर्क क्या है
That is due to when there is alternating current, around that there is alternating flux here. Now what this
अच्छा
flux will do, it will cause an EMF in the conductor or not. Or due to this flux, due to this alternating flux, a reactance will form in the conductor itself. Reactance, X. What is
अच्छा
X? Omega L.
हाँ
L proportional to phi flux. So this flux is alternating, so reactance will form because of frequency component, and due to that reactance inside the center of reactance is very high at the center, because X proportional to L proportional to phi. So flux is
अच्छा
more at the center due to inner conductor is there, and if you come towards surface, reluctance increase. Reluctance
अच्छा
increase air. So most of the reactance is
हाँ
at center. So this reactance will not
हाँ
allow to current flow there. That's why current mostly on surface only.
अच्छा सर और एक डाउट है क्या है कहता सर अभी अभी फर्स्ट क्लास से अभी तक क्लास में आप साइन फंक्शंस ले लिए ना सर क्या है तो भी फॉर एग्जांपल फर्स्ट क्लास से फिर भी फंडामेंटल प्लस थर्ड हार्मोनिक है तो भी E इक्वल टू EM1 sin ओमेगा टी प्लस थर्ड हार्मोनिक E3 sin ओमेगा टी क्या हम कॉस भी ले सकते हैं
Yes, you can
कॉस
take
प्रेफर करके
cos also. Cos also you can take. Both are sinusoidal only. Na? Signals are sinusoidal same, but at zero, sine is zero, but cosine is one. It will start like this. Cosine signals. Anything you can take, but generally we follow sine relations. That's it. No difference.
नहीं का तो हमें पूरा साइनसॉइडल प्रेफर करते हैं ना वेवफॉर्म्स इसलिए आप साइन लिए
Yes, because generally we draw always reference starting from zero like this. This is sine signal.
हाँ
Sine now it is. That's why we proceed with sine.
अच्छा अच्छा क्योंकि कहते सर मैं इंडक्शन मोटर में देखे तो पूरा उन लोग कोसाइन फंक्शंस यूज करे था क्या आप साइन यूज करे फिर भी वो कोसाइन है कुछ डिस्टरबेंसेस
No, nothing, because in induction motor somewhere we take mostly cosine for RMF and all, because
जी
at
जी
starting also there is some value for cosine. At
अच्छा
omega t
हाँ
is
सही
0,
है बात
cosine is having some magnitude, but sine is 0 value.
जी जी
That's why we consider
अच्छा
that one.
हाँ ओके ओके थैंक यू सर थैंक यू
Okay. Next, Abdul Rahman.
Hello, sir.
Tell me.
77F. 17F, sir. In this method, flux and EMF also sinusoidal. Sir, first current is also sinusoidal or not, sir?
Source is sinusoidal only always.
Yes, sir.
Source
This
is
current is also
sinusoidal.
sinusoidal.
Source is sinusoidal. Actual initial flux produce flat top, then automatically it is becoming sinusoidal in this because
Sinusoidal.
of this tertiary winding.
Yes, sir.
5 3 cancelled. So in the core, finally fundamental, EMF induced also fundamental, sinusoidal.
Current is also sinusoidal. Or
Current
not?
also sinusoidal because third harmonic is not flowing in primary here. Observe.
Yes. Yes.
That's why. Good. Yes.
Hello, sir.
Shiva, tell me.
Sir, on page 1F, sir.
Huh?
Page 1F, sir.
1. Okay.
Sir, here on the primary side, can we connect A to B1, sir? I mean, the opposite.
A to B1. That next connection I will show you. That is also we are using. Next delta star it will come.
Okay, sir. Sir, and then the degree is what it represents, sir. I mean, 0 degree,
What?
180 degree.
DD means delta.
No, not DD, sir. Degrees. 0 degrees, 180 degrees. What it represents.
That is angle between primary line voltage, secondary line voltage. So that is importance is only for parallel operation. I will show you what happens with these variations.
Oh.
There.
Sir, in 8F, sir.
Sir?
Sir, in the features of delta connection. Sir.
What?
Features of delta connection. And remove the present.
This one?
Yes, sir. Can you explain the fourth point of this?
Which one? Fourth point.
No, fourth point, yes, sir.
No, so that is nothing but this is only. So in this, if you apply input voltage V1, how much voltage disconnection will be outside? V1 by X, no?
Yes, sir.
That point only we return there.
Oh.
What?
Sir, and then 15, sir. Sir, and here in the second case, can you show me that how the neutral moves? Sir, I don't get it. How the neutral point moves? Sir? You mean the second case? In the first case, I understood.
First case, suppose this is EA1, EB1 fundamental. Okay.
Yes, sir.
Third harmonics also there in this. So when you add both, suppose example I taken third harmonics here is upward, pointing towards upward direction. Just first one is our reference we taken. Now, if you add both, whatever the direction this third harmonic EMFs is pointing, in the same direction, neutral also will shift. So this actual neutral is here. Now I taken this neutral little upward direction. And in the second figure, third harmonics pointing leftward, no, left side. That's why this neutral is shifted like this here, resultant.
So I'll get shifted towards the left, sir?
Yes, from here to here.
Okay, sir.
Like that, neutral is shifted.
Yes, thank you.
Sir?
Tell.
Sir, direction అనేది లెఫ్ట్ సైడ్ ఎందుకు తీసుకున్నాం సార్?
ఏ డైరెక్షన్?
ఒమేగా EA1 నుంచి
అది వెక్టర్ డైరెక్షన్, కన్వెన్షనల్ డైరెక్షన్ కదా, ఆల్వేస్ వి ఫాలో యాంటీ క్లాక్ వైస్. అవి ఇలా రొటేట్ అవుతూ ఉంటాయి వెక్టర్స్.
క్లాక్ వైజ్ ఎప్పుడు వస్తుంది సార్? అంటే
క్లాక్ వైజ్ వి వెక్టర్స్ అనేది ఆల్వేస్ కన్వెన్షనల్ డైరెక్షన్ వి ఫాలో, స్టాండర్డ్ డైరెక్షన్ యాంటీ క్లాక్ వైజ్ తీసుకుంటాం.
ఓకే. సో EM sin ఒమేగా t థర్డ్ హార్మోనిక్ ఫస్ట్ హార్మోనిక్ చెప్పారు కదా సార్, అది కాస్ హార్మోనిక్ కూడా మేము తీసుకోవచ్చు అని చెప్పారు కదా సార్. అంటే ఏ ఈక్వేషన్స్ లో ఎట్లా తీసుకుంటాం సార్ అది?
ఏవి
అంటే దేన్ని బట్టి కాస్ సైన్ అట్లాగా తీసుకుంటాం సార్?
అది మనం పర్టికులర్లీ హియర్ ఇక్కడ మనకి ఎక్కడ కొసైన్ యూజ్ చేయం, అన్ని సైన్ లోనే తీసుకుంటాం. ఓన్లీ ఇన్ ఇండక్షన్ మోటార్స్ లో మనకి RMF కాన్సెప్ట్ ఉంది. సో దేర్ వి విల్ టేక్ కొసైన్ రిలేషన్స్. ఎందుకంటే ఫ్రమ్ జీరో రెఫరెన్స్ తీసుకున్నా దేర్ ఈస్ సమ్ వాల్యూ ఆఫ్ ఫ్లక్స్ నా దేర్. ఆ ఫ్లక్స్ డిఫైన్ చేయాలంటే కొసైనే తీసుకుంటాం, సైన్ కొసైన్. సైన్ అయినా తీసుకోవచ్చు బట్ మోస్ట్లీ వీ ప్రిఫర్ కొసైన్. సో ఇండక్షన్ మోటార్ అయిందా మీకు? లేదు కదా?
అయిపోయింది సార్. అంటే
ఏ బ్యాచ్?
కాలేజ్ ఫైనల్ ఇయర్ అయిపోయింది సార్ ఈ ఇయర్.
ఓకే ఓకే. మీకు ఇండక్షన్ మోటార్లు అడగండి, చెప్తారు అప్పుడు.
ఓకే సార్. సార్ ఒకసారి పేజ్ నెంబర్ 2 తీసుకో సార్. ఇక్కడ డైరెక్షన్ C1 కదా సార్, A2 పక్కన, స్మాల్ A2 పక్కన C1 కదా సార్. స్మాల్ A2 పక్కన C1 కదా సార్, డైరెక్ట్. సార్ C2 అన్నారు.
ఎస్ ఎస్ C1 ఇక్కడ C2 ఉంది కదా ఆల్రెడీ. ఎస్ C1 C2 C1. ఓకే
ఓకే సార్.
Hello. Hello.
Tell me, Bhaskar.
Hello, sir. In the last page, answer, sir. అవి మనం ఫేజెస్ డ్రా చేసినాం కదా సార్, ఫేజెస్ 3 కండిషన్ 0 డిగ్రీ 30 డిగ్రీ.
ఏది చెప్పు
సార్. ఇందులో థర్డ్ కండిషన్ లో మాగ్నిట్యూడ్ ఆఫ్ B1 ఒకటే డిక్రీజ్ అవుతుంది కదా సార్,
90 degrees దగ్గర.
అంటే అది ఓన్లీ B1 కదా సార్ ఇన్ ఫేస్ ఉన్నది హార్మోనిక్స్ కి.
ఏదో ఒకటి జస్ట్ ఎగ్జాంపుల్ లైక్ షోన్ లైక్ దిస్. యూ కెన్ కన్సిడర్ మీరు ఏ పొజిషన్ తీసుకున్నా కూడా దట్ magnitude of phases will be different కదా. The neutral అనేది definitely will shift to some other location. అది చూపించడానికి జస్ట్ ఎగ్జాంపుల్ ఐ టేకెన్ లైక్ దిస్.
ఓకే సార్. ఇది సార్ స్టార్ ఫైల్ లింబ్ ఎక్కడ అంటే ఏ అప్లికేషన్ దగ్గర యూజ్ చేస్తాం సార్?
స్టార్
ఇప్పుడు ఫైల్ లింబ్ అనే ప్రాబ్లం ఉంది కదా సార్ మనకు, డ్రాబ్యాక్. ఆ ట్రాన్స్ఫార్మర్స్ ఎక్కడ యూజ్ చేస్తాం సార్ అప్లికేషన్?
మనం స్టార్ యూజ్ చేయొచ్చు, ఐసోలేషన్ పర్పస్ అయినా యూజ్ చేయొచ్చు. బట్ ప్రాక్టికల్లీ మనకి ఉండే ట్రాన్స్ఫార్మర్స్ అన్ని ఏదర్ డెల్టా స్టార్ కానీ స్టార్ డెల్టా కానీ ఉంటాయి. ఎందుకంటే మనం మెయిన్ పర్పస్ ఆఫ్ ట్రాన్స్ఫార్మర్ ఏంటి? ఏదర్ 2 స్టెప్ అప్ ఆర్ స్టెప్ డౌనే కదా. సో ఫర్ దట్ రీజన్ డెల్టా స్టార్ మోస్ట్లీ వి యూస్ అండ్ స్టార్ డెల్టా ఫర్ సమ్ అప్లికేషన్స్. టుమారో ఐ విల్ షో దట్.
సార్ ఈ వోల్టేజ్ ఫ్లక్చుయేషన్ అనేది ఓన్లీ దిస్ అంటే ఈ ట్రాన్స్ఫార్మర్ లోనే అక్కర్ అవుతుంది సార్ వోల్టేజ్ ఫ్లక్చుయేషన్స్?
yes neutral oscillating కదా. yes only here, remaining all EMF sinusoidal అంటే అక్కడ ఉండదు. ఓకే
సార్. ఇక్కడ పొలారిటీ అనేది అంటే డైరెక్ట్ మనం ఇట్లా జస్ట్ కన్సిడర్ చేసినాం అంతేనా సార్?
ఏ పొలారిటీ? డాట్స్?
అవును సార్, డాట్స్.
that is our bipolarity test we consider that.
ఓకే సార్. బట్ మనం అన్ని ఒకటే సేమ్ యూజ్ చేస్తున్నాం కదా సార్ అన్ని కనెక్షన్స్ లో, అంటే జస్ట్ మనం అట్లా అనుకుంటున్నాం అంతే.
జస్ట్ మనం డాట్స్ అని ఇక్కడ ఉన్నాయి అనుకుంటున్నాం, దట్స్ ఇట్. యూ కెన్ కన్సిడర్ 1 dot here 1 dot here లైక్ దట్. బట్ కనెక్ట్ చేసేటప్పుడు ప్రాపర్ గా కనెక్ట్ చేయాలి.
ఓకే సార్. ఇక్కడ సార్ ఇది మన ఫైలింగ్ సెల్ ఉంది కదా సార్, ఇది ట్రాన్స్ఫార్మర్.
ఇది ఫైలింగ్ ఏంటి?
స్టార్ ట్రాన్స్ఫార్మర్ సార్, ఫైలింగ్. అందులో ఫైలింగ్ సార్, అందులో 3 phases సపోజ్ అన్ని వేరే వేరే 3 డిఫరెంట్ టైప్స్ ఆఫ్ లోడ్ కనెక్ట్ చేసినాం కదా సార్, సింగిల్ ఫేజ్.
yes yes అన్బ్యాలెన్స్ వస్తుంది.
అప్పుడు లోడ్స్ అన్ని అన్బ్యాలెన్స్ వస్తున్నాయి కదా సార్?
yes అన్బ్యాలెన్స్డ్ లోడ్ కి షెల్ టైప్ ఈస్ ద బెస్ట్ సూటబుల్. ఎందుకంటే మనకి షెల్ టైప్ లో జనరల్లీ 3 phase ట్రాన్స్ఫార్మర్స్ లో 3 phases will not have same load కదా. 3 phases will have different loads. Then unbalancing will come, but still that unbalance is withstand by the shell type core. Why? Because whenever there is 3 phases on primary secondary loads are there. Now what is the flux? Different loads means different currents means different magnitude of flux. So whatever resultant flux we are getting, that flux will distribute from empty lanes. Still it is balanced. Still it is balanced. But if you take core type transformer, it is unbalanced. If you take core type, 3 windings are there here: primary, secondary, primary, secondary, primary, secondary. Whenever currents are different, the flux produced is different. Now if you take the resultant of these 3, the resultant flux is not zero, because different magnitude of flux, different some will not be zero. Some zero కాకపోతే return ఉండాలి కదా.
అవును సార్.
Where is return? Through air. So unbalancing will come. But through core here there is a chance. That's why shell type is best for unbalanced loads. Okay.
బట్ ఓకే సార్, అది అన్బ్యాలెన్స్ లోడ్ కానీ వోల్టేజెస్ అని ఫ్లక్చుయేట్ అవుతుంది సార్. ఓకే
అవుతాయి కదా
ఆ టైంలో.
షెల్ టైప్ అయితే అవ్వదు. అన్బ్యాలెన్స్ విత్ స్టాండ్ బై షెల్ టైప్. కోర్ టైప్ లో మాత్రమే అన్బ్యాలెన్స్ వస్తుంది.
ఓకే సార్.
ఓకే Please sir, what tell me.
Sir, I am moving on, sir. That but I am using another. Yeah, no sir, another my another laptop.
Okay,
Sir,
okay.
सर ये आपने स्टार और डेल्टा फीचर्स बताए ना सर. उसके अंदर वी मेरे को रिलेशंस मालूम है. एक बार वो फीचर्स खोलो ना सर. पेज नंबर 12 या 10 में है. हाँ, एक पेज सामने सर. सर इसमें वी फेज इज लेस बोल के बोल रहे हैं और उसमें वी फेज इज ग्रेटर बोल. डेल्टा में वी फेज ग्रेटर, स्टार में वी फेज लेस बोल रहे ना सर. मतलब अपन कांस्टेंट कौन सा लेके कैलकुलेट कर रहे हैं?
VL line KV line voltage I am taking same for both connections. Line voltage.
Okay, line voltage
Based
same.
on that phase voltage is different in both.
और ये करंट भी सेम सर. दोनों में लाइन करंट
let
सेम.
line current 20 amps in both.
Okay, okay.
Then accordingly delta star.
Okay सर, क्लियर सर. सर ये न्यूट्रल शिफ्टिंग आप समझाए ना सर.
हाँ
सर वो आप ये बोल रहे हैं ये फंडामेंटल और थर्ड हार्मोनिक मिले बाद में रिजल्टेंट क्या क्या ऐसा आता बता रहे हैं ना. राइट साइड जो फिगर है ना सर,
हाँ
वो रिजल्टेंट है या ओनली फंडामेंटल है?
हाँ रिजल्टेंट एक्चुअल फंडामेंटल ऐसे नहीं होता ना, सेम मैग्नीट्यूड होना चाहिए. मगर फंडामेंटल का मैग्नीट्यूड क्यों चेंज हुआ? बिकॉज ऑफ थर्ड हार्मोनिक. That's why this is reason. Fundamental it is.
Only fundamental.
I am showing fundamental. Fundamental is different magnitudes. This is due to the effect of third harmonic.
हाँ no, sir, आप ऊपर E equal to E1 plus E3 लिखे ना सर.
This is a fundamental here.
Only E1.
Yes.
Okay, यहाँ अगर अनबैलेंस्ड में ये ऐसा लेफ्ट साइड कैसा रहता, अगर हार्मोनिक रहे तो फंडामेंटल ऐसा रहता बोल के बता रहे.
Yes, yes, yes.
सर ये न्यूट्रल शिफ्ट हुआ बोल के बोल रहे ना सर अपन.
इसका
मतलब ये नहीं कि अपन इन दोनों को ऐड कर रहे हैं.
yes, simple. Just
ऐड तो नहीं कर रहे ना सर, मतलब वेक्टोरियली ऐड नहीं कर रहे ना आप.
approximately we are adding, not vectorially. Just I am showing with
इसको प्लस बोले तो ऐड करे जैसा ना सर.
No, yes, one. We are vector addition only. This is actually E1 plus E3 means vector addition.
हाँ yes sir.
मगर we are directly phasors को ऐड कर रहे हैं ना इधर.
हाँ सर, तो ये रिजल्टेंट रहना ना सर. आप फिर फंडामेंटल.
Okay, you take resultant only. इसका ये क्या हुआ? But I am writing EA1. EA1 plus E3. So simple, you can take E that is.
Okay sir. सर ये न्यूट्रल. हाँ yes sir, वो तो क्लियर हो गया. अब ई न्यूट्रल शिफ्ट हो रहा बोल के अपन स्टेटमेंट बोल रहे हैं, ऐड कर रहे हैं. मतलब हाउ इट इज शिफ्टिंग कुछ भी समझ नहीं आ रहा सर.
यही है ना. इसको अगर फर्स्ट फिगर में लेफ्ट में न्यूट्रल इज हियर.
यस सर.
सेम न्यूट्रल नाउ लिटिल मूविंग टुवर्ड्स अपवर्ड. ना उसके बाद इधर यही न्यूट्रल इधर शिफ्ट हो जाएगा ना, ऐसे शिफ्ट हो जाएगा ना.
हाँ 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 सर. अब ये कुछ भी फेजर्स को अपन ऐड करें तो वो एक पॉइंट तो फिक्स रख के, अब E को E3 ऐड करना है बोलते तो विक्टोरियल ऐड करते हैं, लेकिन वो सेंटर पॉइंट तो वहीं रहता ना सर. लेकिन अपन क्या कि उसको चेंज कर रहे हैं, वो मेरे को समझ.
ओके ऐसे ये आई अंडरस्टैंड. बट मैग्नीट्यूड ऑफ वोल्टेज ले लेना अगर डायरेक्टली इन ईच फेज मैग्नीट्यूड ऑफ वोल्टेज. Generally you can consider in this first case में omega t equal to 0 में this third harmonics is in phase with EA1 no?
हाँ
Now
सर
as it is in phase किसका magnitude बढ़ जाएगा for example
EA का बढ़ जाता है
EA का बढ़ जाएगा you take like that EA is increased then EB EC will decrease no?
हाँ सर मैं वही बोल रहा हूँ मतलब मैग्नीट्यूड्स बढ़ते और घटते हैं बट पॉइंट तो वहीं पर रहता ना सर पॉइंट ही अपन चेंज कर रहे हैं
because I am showing that for easy understanding neutral is shifting whenever E3 is pointing along the direction so ऐसे भी understand कर सकते हैं
सर एक अनबैलेंस्ड सिस्टम के वेक्टर डालो सर बाजू ऊपर डालो सर
unbalanced means
अनबैलेंस सिस्टम में फेज एंगल मतलब मैग्नीट्यूड्स इक्वल नहीं रहते एंगल सेम नहीं रहते
okay at EA1
ना मैग्नीट्यूड्स ले लो सर सीधा एक 20
first I taken angles or magnitudes
ओके ये बैलेंस्ड है सर ये बैलेंस्ड है अब एक
unbalanced means you can take EA1 EB1
हाँ सर
EC1 this is not having exactly this is let some 90 degree this is some 110 degree like the different angles
yes sir.
and magnitudes also different this is unbalanced system
सर एंगल्स के कि 120 120 120 रह के सिर्फ मैग्नीट्यूड्स अलग-अलग रहे तो भी उसको अनबैलेंस्ड बोलते हैं ना सर
yes unbalanced only
वो केस ले लो सर आप मतलब मैग्नीट्यूड सेम
this is EA1
हाँ यस सर ये
EB1 EC1 different magnitudes
अब ये फिगर और अपने अपन जो प्रीवियसली आप जो एक्सप्लेन करे वो फिगर दो भी सेम हो रहा ना सर
हाँ सेम
हाँ इसमें अपन क्या कर रहे हैं ईए का मैग्नीट्यूड ज्यादा है बोल के बोल रहे हैं लेकिन वहां पे क्या बोल रहे हैं न्यूट्रली शिफ्ट हुआ बोल रहे हैं मतलब टर्मिनोलॉजी दोनों का अलग है लेकिन फिगर सेम है ना सर
यस सेम so anyhow finally what is our observation unbalanced तो आता है ना
हाँ सर अनबैलेंस्ड तो रहता है
that's it enough
सर ये how to reduce that how to avoid that neutral shifting तो अपन स्टार source side स्टार लोड साइड ग्राउंडिंग कर दे
this is one method ना neutral grounding
हाँ मेथड ये सेकंड मेथड है फर्स्ट मेथड
load side is not necessary load side not necessary if you have good path for third harmonic current on primary enough but generally we consider load side also for better okay
एक तरफ अगर कम एक तरफ का I3 के मतलब थर्ड हार्मोनिक करंट्स के लिए अच्छा रेजिस्टेंस लो रेजिस्टेंस पाथ
लो रेजिस्टेंस रिक्वायर्ड
लोड लगाए तो भी जरूरत नहीं है
not required
सर आप यहाँ पे Z1 का इक्वल सर डिनोमिनेटर में मतलब थर्ड हार्मोनिक करंट को थर्ड हार्मोन मतलब नेगेटिव सीक्वेंस इंपेडेंस या जीरो सीक्वेंस इंपेडेंस ही चाहता ना Z3 plus ZG plus ZL आता ना
that is unbalanced में ना negative and zero sequence
हाँ सर मतलब I3 तो जीरो सीक्वेंस कंपोनेंट है ना सर
हाँ yes
तो E3 by Z0
what you can take but example I shown because of this high impedance magnitude is reduced here we are not discussing now what total क्या बोलते हैं वो पावर सिस्टम में
हाँ नहीं कर रहे लेकिन वो ये लिंक कर रहा हूँ सर जस्ट सिर्फ मैं सर उसके बाद नेक्स्ट
अनसिमेट्रिकल कंपोनेंट्स
हाँ सर नेक्स्ट पेज जाओ सर जरा वो सेकंड पॉइंट बोला ना सर हाँ इसमें सर ये यहाँ पे I3 का मैग्नीट्यूड क्या आता है सर E1 plus E2 plus E3 मतलब E plus E plus E by Z3 plus Z3 plus Z3 मतलब
whatever we have seen in yesterday's class I3 equal to E3 by Z3 that is only same
sir I have written correct
okay
sir one more sir 15 16 17 okay sir done sir thank you
sir సార్ వెక్టర్ డయాగ్రామ్స్ లో ఇప్పుడు తీసుకుంది అన్బ్యాలెన్స్డ్ బ్యాలెన్స్డ్ సార్
ఏది రిజల్టెంట్ ఓన్లీ ఫండమెంటల్
రైట్ సైడ్ లో సార్
అది అన్బ్యాలెన్స్డ్ కదా వోల్టేజ్ ఈస్ చేంజింగ్ కదా మాగ్నిట్యూడ్స్
అది పాయింట్ అనేది చేంజ్ అవుతుంది కదా సార్ అందుకు అన్బ్యాలెన్స్డ్ కదా సార్
yes అదే వోల్టేజ్ ఫ్లక్చుయేషన్ అంటే అన్బ్యాలెన్స్డ్ కదా
సార్ థర్డ్ హార్మోనిక్ లో మనం అట్లా గీసినప్పుడు ఫిఫ్త్ హార్మోనిక్ లో ఎట్లా గీస్తాం సార్ వెక్టర్స్
అది నెగటివ్ సీక్వెన్స్ తీసుకోవాలి
ఒకసారి చెప్తారా సార్
సపోజ్ ఇది పాజిటివ్ కదా EA1 EB1 EC1. So when there is negative sequence, then what is negative sequence means? Suppose I'm taking here EA5, this is EB5, this is EC5. అంటే ఇక్కడ రెండు ఇన్ ఫేజ్ ఉన్నాయి కదా, ఈఏ మ్యాగ్నిట్యూడ్ ఇంక్రీజ్ అవుతుంది. ఇప్పుడు EB5 EC5 రెండు ఇన్ ఫేజ్ లో ఉన్నాయి ఈ రెండు. సో as both are in phase, you find resultant magnitude is how much? EB5 కనుక్కోండి, EC5 magnitude, EC1, EB5 EC1. Find magnitude vectorially and then check how much it is. Draw here. Similarly, draw this. So you will get unbalanced again.
సార్ బ్యాలెన్స్డ్ ఎప్పుడు వస్తుంది సార్? అంటే
బ్యాలెన్స్ అంటే ఓన్లీ ఫండమెంటలే ఉండదు. హార్మోనిక్ షుడ్ నాట్ బి దేర్.
ఈ హార్మోన్ హలో
వెంకట్
సార్, హార్మోనిక్స్ అనేవి వెన్ లోడ్ కనెక్ట్ చేసినప్పుడే వస్తాయా సార్?
లోడ్ లేకపోయినా ఏ కనెక్షన్, అది కనెక్షన్ ని బట్టి కదా. ఫస్ట్ స్టార్
స్టార్ లో తీసుకున్నప్పుడు సార్,
స్టార్ లోనే మనకి ఓన్లీ ఫర్ షెల్ టైప్ లోనే ద ఈఎంఎఫ్ ఇండ్యూస్డ్ ఈస్ నాన్ సైనూసోయిడల్. ఫర్ దట్ వీ హావ్ ద మెథడ్స్ న్యూట్రల్ గ్రౌండింగ్ అండ్ టెర్షియరీ. వన్స్ యూ ప్లేస్ టెర్షియరీ వైండింగ్ ఆల్వేస్ సైనూసోయిడలే ఉంటుంది, మీరు లోడ్ కనెక్ట్ చేసినా కనెక్ట్ చేయకపోయినా.
if in case delta to delta తీసుకుంటే
delta always sinusoidal, no problem, because delta providing path for third harmonic current kada directly.
అంటే whenever under no load on
anything, any condition,
load.
any condition.
Okay, thank you sir, that's it.
Tell me, Anil Kumar.
Sir, good evening, sir.
Good evening. Tell me.
Sir, 1F.
Which one?
1F slide, sir. Sir, could you explain this node point, sir? Node point and
Which one?
Node, sir.
Voltages? Node. So this is simple. Let us considering N1 by N2 means, what is N1 by N2? We call turns ratio, no? That is taken as EX. Now we have the transformation relation is this. Now from this we return E2 phase equal to E1 phase by X. N2 by N1 means 1 by X. So that relation we are using in all these connections.
X is to 1.
X is turns ratio.
Yes, sir. Okay, sir.
Sir, in 16F, sir. No, 15F, sir. Sorry, 15. సార్ ఇక్కడ థర్డ్ హార్మోనిక్స్ వచ్చేటప్పుడు అది 0 degree యాంగిల్ ఉంటుంది. అప్పుడు ఇక్కడ E1 ఫండమెంటల్ హార్మోనిక్ ఒకే లైన్ మీద ఉండాలి కదా సార్, ఎందుకు సార్ పైకి షిఫ్ట్ అయింది?
నేను చెప్పేది అది, దీని నో నీడ్ టు కాన్సెప్ట్, దీని మీద అంత కాన్సన్ట్రేషన్ అవసరమే లేదు. జస్ట్ ఐ గివ్ ఎన్ ఎగ్జాంపుల్, వెన్ ఎవర్ బోత్ యాడెడ్ న్యూట్రల్ ఎలా మూవ్ అవుతుంది అనేది చూపించాను జస్ట్ అంతే. ఈ యాక్చువల్ గా బోత్ ఇన్ ఫేజ్ కదా, అప్పుడు EA1 ఎక్కువ ఉండాలి అకార్డింగ్ టు ఫిగర్, ఎందుకంటే EA3 EA1 ఇన్ ఫేజ్ ఉంది కదా. సో బట్ ఐ విత్ రెస్పెక్ట్ టు థర్డ్ హార్మోనిక్స్ బట్టి నేను న్యూట్రల్ ని షిఫ్ట్ చేశాను, జస్ట్ టు షో న్యూట్రల్ ఇస్ షిఫ్టింగ్ లైక్ దిస్. మ్యాగ్నిట్యూడ్ ఏదైనా ఇంక్రీజ్ అవ్వచ్చు, వాట్ ఎవర్ ఇట్ ఇస్. ఓకే
సార్, అంటే ఇప్పుడు 2 వెక్టర్స్ సేమ్ డైరెక్షన్ లో మూవ్ అయితే దాని యొక్క వెక్టర్ అడిషన్ వచ్చేసి రిజల్టెంట్ వచ్చేసి దాని యొక్క డిఫరెన్స్ అవుతుందా సార్? ఆ రెండిటి యొక్క డిఫరెన్స్
అది డిపెండ్స్, ఇంక్రీజెస్ కదా బోత్ ఇన్ ఫేజ్ కాబట్టి. 2
ఇప్పుడు
వెక్టర్స్
ఇక్కడ
సేమ్,
ఈ ఫిగర్ లో బోత్ ఇన్ ఫేజ్ అంటే అప్పుడు EA1 ఇంక్రీజ్
yes
అవుతుంది, అదే
EA1
రిజల్టెంట్
increase,
ఇంక్రీజ్ అవుతుంది.
అలానే డ్రా చేయాలి, బట్ నేను అలా డ్రా చేయలేదు. సో ఐ హావ్ షోన్ న్యూట్రల్ ఇస్ షిఫ్టింగ్ అకార్డింగ్ టు థర్డ్ హార్మోనిక్స్. ఆ ఎఫెక్ట్ ని బట్టి షిఫ్ట్ అనేది చూపించాను జస్ట్ ఫర్ ఎగ్జాంపుల్. ఓకే
ఓకే సార్. నెక్స్ట్ పేజ్ సార్, ఇన్ 16. సార్ ఇక్కడ మనము స్టార్ లో గ్రౌండెడ్ లో ఇప్పుడు ఈ న్యూట్రల్ పాత్ పెట్టినా మనకి I3 అనేది స్మాల్ గా ఉంది కాబట్టి ఫ్లక్స్ అనేది అంటే ఈఎంఎఫ్ అనేది పీకి వేవ్ అవుతుంది కదా సార్.
కంప్లీట్ గా సైనూసాయిడ్ రావట్లేదు.
అప్పుడు నేను ఎస్టర్డే క్లాస్ లో చెప్పారు కదా సార్ స్టార్ కనెక్షన్ విత్ గ్రౌండెడ్ లో, అప్పుడు అక్కడ కూడా మీరు జస్ట్ న్యూట్రల్ ఉంటే సరిపోతుంది సోర్స్ ఇక్కడ
ఎస్
అని
అక్కడ
చెప్పారు కదా సార్.
జస్ట్ అక్కడ స్మాల్
tertiary better
ఇన్ఫర్మేషన్, ఎస్ అక్కడ స్మాల్ ఇన్ఫర్మేషన్ ఇఫ్ యూ ప్రొవైడ్ పాత్ ఫర్ కరెంట్ యూ కెన్ మేక్ ఈఎంఎఫ్ సైనూసాయిడల్ అన్నాం. బట్ ఇక్కడ క్లియర్ గా చెప్పాం కదా జస్ట్ ఓన్లీ న్యూట్రల్ గ్రౌండింగ్ నాట్ సఫిషియంట్. టెర్షియరీ వైండింగ్ పెడితేనే వీ గెట్ కంప్లీట్ సైనూసాయిడల్. ఓకే
సార్ ఇంకొక డౌట్ సార్, ఫైవ్ లింబ్ షెల్ కోర్ టైప్ ఉంది కదా సార్ ట్రాన్స్ఫార్మర్, అక్కడ మనకి E3 నుంచి నెక్స్ట్ I3 ప్రొడ్యూస్ అయ్యి మళ్ళీ I3 నుంచి 5-3 ప్రొడ్యూస్ అయ్యి ఈ 5-3 ఫస్ట్ ప్రొడ్యూస్ అయిన 5-3 ఈ రెండు కంపన్సేట్ అయ్యి మనకి కరెంట్ అనేది పీకి వచ్చి నెక్స్ట్ ఈఎంఎఫ్ సైనోసాయిడల్ వస్తుంది కదా సార్, అది డిసడ్వాంటేజ్ అక్కడ రాదన్నారు కదా సార్ మీరు.
అంటే షెల్ టైప్ లో గ్రౌండింగ్ ప్రొవైడ్ చేస్తున్నామా లేదా అది కదా ఇంపార్టెంట్. గ్రౌండింగ్ లేదనుకో అప్పుడు I3 ఎక్కడ ఫ్లో అవుతుంది అసలు? అర్థమైందా?
జీరో అయిపోతుంది.
అందుకని
అర్థమైంది.
सर ये फाइलिम शेल टाइप कोर के एडवांटेजेस ये अनलोडिंग फर्स्ट पॉइंट के अनलोडिंग है सर, मतलब अनलोड लोड अनबैलेंस्ड रह చెప్పి इन्हें फ्लक्स को कॉम्पनसेट कोर में रोटेट होता आप बोले ना सर अभी, उसके सिवाय और क्या एडवांटेजेस है सर?
only that shell type whatever we have seen single phase transformer like leakage flux is less, ये सब advantages.
प्रैक्टिकली अपन कौन सा इस्तेमाल करते सर, कोर टाइप या शेल टाइप सर?
both for some high voltage application we go core type, but for low voltages we go shell type, and all distribution mostly shell type only. Okay, so I'm stopping today and tomorrow also we have same time. Good night
सर. लास्ट वन सर.
both.
सर ये डेल्टा अपन टेरिशरी वाइंडिंग लेते ना सर, ये हर प्रैक्टिकली अब जितने भी अपन बाहर देखते हैं सब में रहता सर, ये मतलब स्टार नॉट इन ऑल स्टार ट्रांसफार्मर जहाँ भी है प्रैक्टिकली उन सब में डेल्टा रहता सर.
Yes, tertiary winding will be there.
Okay.